Hello everyone, welcome to IMS GATE Academy. I am Atul Negi, faculty of IMS GATE Academy, and today we are here to discuss theory of machine, and in this session we'll be discussing the complete important formulas, important concepts, right? And we'll quickly revise our theory of machine chapter subject, right? So please be ready with your notebook and please note down all those important concepts, right? Important formulas. And in this session, see, topics, obviously important topics will focus, but we'll also see from which topic you can expect the numericals, right? We'll also see that numericals. Okay everyone, so we'll start the session quickly everyone. Okay, so these are the topics that will start here. Okay, we'll start with simple mechanism, then we'll go with flywheel, gate train, balancing, governor, gyroscope, vibration, and cam and follower, right? Now if I talk about the important chapters here, in which you will expect, definitely for sure you will expect some numericals, right? So for example, like if I talk about this simple mechanism, this is one of the most important topic. Definitely you can expect numerical. After that, this gate train and this vibration part, right? These are the most important topic. A very good evening, Saurav. Most important topics of the theory of machine subject, right? So definitely you can expect the numericals from this one. Now after this, if I talk about the flywheel, balancing, governor, gyroscope, and cam and follower, these are equally important, right? We cannot say that balancing is more important as compared to flywheel, right? So all are equally important, okay? But in nutshell, if I to say, these three topics are what? Very important. Okay everyone, right? So we'll start with simple mechanism. We'll start with simple mechanism. Okay, we'll start with the simple mechanism, right? So first of all, degree of freedom, right? So most important topic in the simple mechanism, the degree of freedom, right? So we'll write down the formula here first of all, and we'll discuss the important things. Generally student will do mistake in writing the formula also, right? And what are the important things that we need to take care, okay, while putting the values in the formula also. Okay everyone, now see, if I talk about the degree of freedom formula, right, so it will be like this: 3n minus 1 minus 2j minus h, right? I hope everyone knows this formula, right? This is the general formula, right? Now if I talk about the modified form of this formula here, that will be the modified form. It will be like this: 3n minus nr minus 1, okay, minus 2j minus h minus fr. So this is the modified form of the degree of freedom formula. Okay everyone, now if I talk about in the modified formula and this main formula also, you should remember n is what? The number of links, right? J is what? The number of binary joint. H is what? Number of higher pairs. Now what is nr and this fr? nr is the number of redundant degree of links, okay, that we have to subtract while counting the number of links. Okay, remember this point. Now if I talk about fr, fr is the redundant degree of freedom, right? Redundant degree of freedom basically means any of the link can have the motion without affecting the other links. So if there is such kind of a motion is possible, so we'll call that motion as redundant degree of freedom. And what is redundant link here? Those links which do not affect the mechanism, right? So complete motion is there in the mechanism, but that particular member is not affecting the motion of mechanism, right? So in that case, we call that link as redundant link. Remember this point. So redundant link will not count in the number of degree of freedom formula, and fr will not count in degree of freedom, right? So this formula you need to remember, guys. This formula, okay, this formula you need to remember, very very important. Okay everyone, so in a meanwhile you should take a copy and write down each and every important formulas here. Okay everyone, now come to the next part here. Okay, next, Grashofs law. Okay, again in many of the previous year questions you will see a Grashofs law they have asked, right? Now when we solve the Grashofs law, everyone knows the basic definition, but they will miss one important point here. Okay, what is that point? See, everyone knows that the smallest plus longest link length should be less than equals to other two link length, summation of other two link length, right? This is the basic format of the law. Everyone knows that, but what they forget actually is this law is applicable for 4-bar mechanism, right? And what is their 4-bar mechanism? All the pairs are the turning pairs. All the pairs are the turning pairs. That point you should remember always, right? I think in the GATE 21 or even 22 also, they have asked one question here. I think in the last year only, they have asked one beautiful question in which one of the pair is what? The sliding pair. Okay, so directly you cannot apply the Grashofs law in that particular mechanism. You have to replace the this prismatic pair or the sliding pair with the revolute pair or the turning pair. Then only you can apply the Grashofs law. This is the most important point, guys, right? So smallest plus longest link length is less than P plus Q, then obviously the Grashofs law will be valid, right? And we'll write here applicable for four-bar mechanism. Applicable for 4-bar mechanism only. So you have to ensure whether all the pairs are turning pair or not, right? All the pairs are the turning pair or not. That point you should remember always. Okay, otherwise you cannot apply this particular law. Okay, everyone. Now tell me, is there any doubt? Is this point clear, everyone? Yes or no? Everyone should tell. Clear? Okay, great. So this law is applicable for 4-bar mechanism. Now, what are the different cases that we should remember here? Okay, the case number 1, if I talk about the case number 1. Okay, let's suppose draw some 4-bar mechanism here like this. Right, and let's suppose this link is what? Fixed. Okay, this link is fixed. Clear, everyone? So this is a 4-bar mechanism. What you need to understand, first of all, if this law is applicable, then 3 different cases will be possible. Case number 1, in which smallest plus longest will be less than P plus Q. Okay, in this case you need to identify which particular link is what fixed. Based on that only we will define, okay, this type of mechanism will be there. Okay, so first of all, if the smallest link is fixed, what kind of mechanism you will get? Tell me fast. What kind of mechanism you will get if the smallest link is fixed? Okay, I'm writing here smallest is fixed. Okay, this is the first case. Okay, the second point, adjacent to smallest is fixed. Adjacent to smallest is fixed. Third, opposite to smallest is fixed. Opposite to smallest is fixed. So these are the 3 cases, right, everyone? These are the 3 cases that you need to understand. Now let's suppose smallest is fixed. What will happen? Double crank mechanism you will have. Okay, double crank mechanism you will have. Now what will happen if adjacent to smallest is fixed? Crank rocker mechanism you will see. Crank rocker mechanism you will see. And if opposite to smallest is fixed, double rocker mechanism you will see. Okay, so here the crank rocker, then we will have a double rocker. Clear, everyone? So these 3 results you have to directly remember. Okay, so what they will give you, what kind of questions they can frame here? They will give different dimensions here in the 4-bar mechanism, and obviously see, you can see which particular link is fixed, right? First of all, check whether Grashofs law is valid or not. If it is valid, then consider this case if it is possible, right? Now if this case is possible, these 3 sub cases will be there. These 3 sub cases will be there that you understand, right? Smallest fixed, adjacent to smallest or opposite to smallest fixed. Either of the three, from these three cases, either one case will be there, whatever they have given in the question, right? So you have to understand which particular link is fixed, and accordingly we will select this kind of mechanism will be there. Now second thing, second point, second possibility. What is the second possibility here? Okay, what is the second possibility? Okay, right, now see, smallest plus longest equals to P plus Q. Again, see, previously what we have said, small plus longest is less than P plus Q. Now it is equals to, again the law is satisfied. Again the law is satisfied, right? Now see, this can be possible in two different ways, right? What are those? See, let's suppose example 1, if I am taking 2 plus 5, 3 plus 4, right? Obviously you will get the 7, but all the link length are different. All the link length are different, right? So if this particular case is there, this previous case 1 will again repeat. How? See, this case is there, you have to identify whether all the link length are different or not. Okay, you should mention here all link length is different. All link length is different, correct? Okay, now see, now if it is there, again you will say, sir, case A, case B, case C will be there, in which you have to say if smallest fixed adjacent to smallest, again we have to write adjacent to smallest, right? Then what we have, opposite to smallest, opposite to smallest. Okay, like these three different cases again it will be there. Now result will be same, right? Double crank, I'm just writing DC here, double crank, here crank rocker CR, here double rocker you will observe, double rocker you will observe. Now okay, adjacent to smallest fixed, opposite to smallest fixed, like that. Okay, yes, fixed. Clear? Now I hope this case is clear, everyone. Now understand the case, in this case only, case 2, the other example of the case 2, here we'll write example 2. See, again we have this smallest plus longest equals to P plus Q. This can be happen, right, like this, 2 plus 5, 2 plus 5, or you can say, sir, 3 plus 4, 3 plus 4. Okay, like this case will also be possible, where there are equal pair of link. There are what, two pairs you will see which are having equal lengths, right? Now how you will draw the diagram here in this case? See, like this I can draw. This is the one possibility. Another possibility will be like this. Okay, now see, try to understand, very important point. Here the longest link length are there, here it is smallest, here it is smallest, this is longest, and this is also longest. Now try to understand, very important point. In this case the smallest, or I can say the equal link length are placed opposite to each other. Here the equal link length are what, placed adjacent to each other. This kind of mechanism is known as the parallelogram linkage. This kind of mechanism is known as deltoid linkage, right? Remember this point. Deltoid linkage. Okay. Now quickly tell me what will happen if I fix the smallest one, in this case parallelogram linkage. Now quickly tell me what will happen if I fix the smallest link here in this case. Everyone please tell me fast. what will happen if I fix the smallest link length in the case of parallelogram linkage? Double, yes, obviously. See, if you fix smallest or the longest, okay, it doesn't matter actually. In the case of parallelogram linkage, it doesn't matter at all if you fix the smallest or the longest. You will get the double crank mechanism only. And one of the application of this kind of mechanism is what? The locomotive vehicle. Okay, locomotive vehicle we are having, right? Specifically in the trains, if you observe, right? So in the case of parallelogram linkage, any link if you fix smallest or the longest link length, any link you fix, you will get the double crank only in all the cases, right? So we can write here double crank. Okay, we are writing double crank. Now what will happen if in the deltoid linkage smallest is fixed? Quickly tell me fast, guys. What will happen in the case of deltoid linkage if smallest is fixed? Everyone fast tell me. Smallest fixed and another case will be longest fixed. Okay, see, when I say smallest fixed, here in this case also double crank you will see, and here the crank rocker kind of mechanism you will see. So this deltoid and the parallelogram linkage is the most important case here. You should remember, right? Directly in the exam they can frame a question like MSQ, they can frame from this Grashofs law. That is a possibility is there. They can frame MSQ, right? You know that in the GATE examination they have added one type one of the type of question is what? MSQ. Earlier we are having NAT and MCQ only. Now we are having MSQ also, in which more than one options will be correct. Possibility is there. So for that, this topic is what very important, Grashofs law, right? So I hope this point is clear, everyone. So we have discussed case 1, then we have discussed the case 2, in which two examples, two possibilities are there. All link length is different, but in this case the equal pair of link length will be there. Okay, now the case number 3, when the Grashofs law is not satisfied, in that case you will have the double rocker kind of mechanism. Double rocker kind of mechanism you will have if the Grashofs law is not satisfied. I hope this point is clear, everyone. Yes or no? Okay, now see what kind of mechanism we have to see as far as our simple mechanism syllabus is concerned. Okay, for the GATE examination, 4-bar mechanism, single slider crank mechanism and a double slider crank mechanism. These three mechanisms are what very important for the GATE examination. Now we'll see what kind of questions they can frame. Okay, what kind of questions they can frame from these three mechanism, and what are the concepts, what are the formulas, what are the relations that will help you to solve such numericals, right? We will look at those formulas also, right? Now see, first of all, transmission angle. Okay, first we'll discuss this transmission angle. That possibility is there from the 4-bar mechanism. They can ask what is transmission angle. Calculation of transmission angle is also there. So they can they can frame a numerical from this transmission angle topic. Now see, so first of all consider a 4-bar mechanism like this. Right, so this is let's suppose you are having a, okay, let's suppose these are the turning pairs first of all. Okay, these are the turning pair. Now you should understand. Okay, first let's suppose if I show you the input link. This is my input link. Okay, and this is my output link. This is my output link. Clear, everyone? Okay, so input link, output link, right? Now you should understand this point, a very important point. So this input link is there, this output link is there. Generally we'll call this link as the coupler here. Okay, so whatever angle you are having between this coupler and the output link, let's suppose we call it theta here. So this theta is our transmission angle. Always remember this point, whatever configuration is there for the 4-bar mechanism, you have to look for output link, you have to look for the coupler, and whatever the angle is there between them, that particular angle is known as the transmission angle. Clear everyone? This point you should remember. Whatever kind of configuration they have given to you, okay? So angle between output link and the coupler is the transmission angle. Now they will ask a question like that, what is the transmission angle? Let's suppose this obviously this input link is having angle, let's suppose it is having angle alpha. For example, what is my transmission angle if alpha is 0? What is my transmission angle if alpha is what? 180 degree. Okay, so such kind of possibilities they will create and they will ask the transmission angle. Now in order to solve such questions of transmission angle, which important property you should know? The sine rule, cosine rule. Most importantly, cosine rule you should know first of all. Cosine rule you should know, then only it is possible to solve the transmission angle, because there will be a formation of triangle. In the triangle you should be able to calculate the angle, right? So for that, cosine rule is what very important. So I will quickly tell you what is the cosine rule here. Okay, now let's suppose if this is a triangle you are having, this is A, this is B, this is C. Okay, A is the side and opposite to side A angle is alpha, opposite to side B angle is beta, opposite to side C gamma, right? This is the point. Now please everyone, if I have to write, let's suppose this side A is there, if I consider the side A, so A square can be written as B square plus C square minus 2 into B into C cos angle opposite to A is what? Alpha. So we'll write alpha here. So like that we can use cosine rule, and this cosine rule will help you a lot in many problems of design. Okay, not only in theory of machine, in strength of material, in engineering mechanics, in machine design, you can use this kind of relation here. Okay, so now what kind of triangle? See, in place of side ABC, you can have the force, you can have the velocity, you can have the acceleration, momentum, any kind of vector you can have for the triangle, right? So this is the one way. Or if I have to write B, what I will write here? B square will be equals to A square plus C square minus 2 into A into C cos. Here angle will come which is what? Just opposite to B, that is beta here. And in a similar way I can write C square also, like A square plus B square minus 2 into AB into cos. Angle opposite to C is what? Gamma. So we'll write gamma here. So like that we will use this cosine rule in order to calculate the transmission angle. I hope this particular point is clear. So definitely they will give you some condition. They will give you a configuration. From according to that configuration you will have a triangle formation here. You will have a triangle formation. Now let's suppose if I say if alpha is 0, so this link will be here itself. Okay, if alpha is 0, so obviously triangle formation is there. Triangle formation is there. And if I say you if angle is 180 degree, in that case also the triangle formation is there. So in triangle this cosine rule will help you a lot, right everyone? Now moving forward here, next thing, the inversion part, very important. Okay, at least you should remember the names here. Okay, at least you should remember the names. Inversion of single slider crank mechanism, right? I hope you know what is single slider crank mechanism here. Now if different link is fixed, so different kind of mechanism you will get, right? So now if I fix cylinder, you will get IC engine, reciprocating compressor. That is a very common thing you should know. Crank fixed, Whitworth and the rotary engine. Now here this Whitworth is important. Why? Because directly numerical they will ask. From the Whitworth. Okay, we'll see this Whitworth later here. Next, connecting rod fixed, crank slotted bar, QRM. That is what? Quick return motion mechanism. This is also important. From this already they have asked many questions, many numericals they have asked in this case. And if piston fixed and permanent bull engine, these are the examples that you should remember. Okay, now crank slotted quick return motion mechanism, which questions they can frame here? Find the quick return ratio here, QRR. Find the value of QRR, right? And what is QRR? It is the ratio of time for the cutting divided by time for return stroke. Okay, that is what the formula or the concept behind QRR. So first of all, understand the crank slotted bar quick return motion mechanism. What are the links? What are the links? First of all, you should understand, right? Okay, Anubhav will discuss that thing also. Just please be focused in the session what we are discussing, but we can discuss that thing also, no problem. Or better, you can ask that question in our doubt solving portal also, right? That is also there. But we'll continue in this flow only. Okay, now see, crank slotted quick return motion mechanism, right? Everyone, here the link one, first of all, you should understand. What is the link one? Link one is the connecting rod which is fixed here. Connecting rod. See, this is the connecting rod, right? Which is what fixed. In the diagram, they have not shown, but it is a fixed link, right? So this is connecting rod which is fixed. Link number two. Link number two is the driving crank. Okay, or simply I can say crank here. Okay, crank. This part. Link number three. Link number three. Here, what is link number three? Slotted bar. Right, and link number four. The link number four is this slider. Now, I hope this is clear. Now, this link, this member is not a part of mechanism. Actually, we have attached this particular attachment here. We have used this attachment here with our mechanism so that we'll get some output here. Okay, what is the application of this kind of mechanism? We will use such kind of mechanism in our cutting operations, right? So that we can increase our productivity. How we can increase the productivity? Just think about it. During the cutting, some time is required. But when the tool is not performing any cutting operation, definitely that time we have to reduce. Okay. So for that only we are using this kind of mechanism. Now, what questions they will ask? Right. So this is the mechanism here. What question they will ask? They will ask the QRR. So you should understand this is what time for cutting divided by time for return. Okay, and obviously that time will be proportional to the angle. So you can say theta of cutting, theta of return. Now, how it is proportional here? See, as the angular velocity is constant, so you can say theta is proportional to time t. Right, everyone? Now, see, try to understand. This diagram is what very important in order to calculate the QRR, right? So, first of all, understand this is what we are having as the extreme position of the slotted bar. This is again the extreme position of the slotted bar. Because what will happen, this slotted bar will oscillate like this, about this point, right? The slotted bar will oscillate like this. Okay, so these are the extreme position of the slotted bar. Clear, everyone? Now, you should understand very important point. This is the extreme position of slotted bar. What is the extreme position of crank? This is the extreme position of crank. So, this slotted bar will be moving like this during cutting operation, then again come back for the return stroke. But a crank is having complete rotation. So, try to understand this point here. So, this angle is actually the angle of cutting. I will call that angle as alpha here. That is what a usual notation we are using. And this angle, remaining angle is what? The beta, which is the angle during return stroke. And I can say this is what the beta by 2 we are having. Okay, and this is also what? Beta by 2. Like this. So just you need to draw this extreme position diagram and you can easily solve for the QRR because we have to calculate alpha and beta. Right. So now if I just draw the extreme position diagram here, okay. Now see. So these are the two extreme position of the crank and the two extreme position of the slotted bar, right? Now see, right? So this is what we are having as a connecting rod, which is fixed. This angle is beta by 2. This angle is what? Beta by 2, right everyone? Now see, this angle will be 90 degree because rotation will be there. So this slotted bar will be acting as a tangent for the circle. So obviously 90 degree will be there. So I can write here, see, this is the angle 90 degree, this is the beta. So you can use cos beta by 2, base upon hypotenuse, okay? So for that, this is the perpendicular, this is the base. Base will be what? The crank radius. And what is the hypotenuse? This one. This one will be the hypotenuse, okay? Is this point clear, everyone? Is this point clear? So this is the perpendicular here, this is the base, this is the hypotenuse. Hypotenuse is the connecting rod. Okay, I hope this point is clear. Now, if the crank radius is given and if the connecting rod is given, so you can directly calculate the beta. And if beta is there, you can easily calculate alpha also. How? Just by using this relation, alpha plus beta, 360 degree. Clear, everyone? So just by using this extreme position diagram only, you can easily solve the QRR. How? First, this cos beta by 2 relation you have to use. For that, this crank radius connecting rod you should know, and it will be given in the question itself. And using this relation, beta or alpha can be calculated easily. Okay, I hope this is clear. Now, next mechanism, Whitworth. In the GATE 2021, they have asked for the first time in the GATE examination. They have asked for the first time this Whitworth quick return motion mechanism. Okay, only one numerical till now they have asked. So possibility is there they can ask more number of questions from this Whitworth quick return motion mechanism. So you have to be what? Very careful while solving such questions. Okay, because first of all you have to visualize the mechanism, right? You have to visualize the mechanism, then only you will be able to understand what angle is the cutting angle, what kind of angle is they are calling it as a return, because we have to take the ratio. So we have to first aware how the angle has been measured, right? Now in Whitworth quick return motion mechanism, what is happening here? It is kind of a rotation to rotation motion transfer, right? Earlier in the crank slotted, oscillatory to rotary motion is there, or rotary to oscillatory we can say, but in this case double crank to crank you will say, a double rotation is there, rotation to rotation motion will be there. Now here what will happen? Your crank is fixed, yes, that is correct, crank is fixed, but the connecting rod will act as a driving crank. Clear, everyone? No, I will mention you here. Now see, this is what we are having as the connecting rod, which is acting as a driving crank, right? It is acting as a driving crank. It is acting as a driving crank. Clear, everyone? Now this is what we are having as a crank, actual crank, which is fixed. Which is fixed. Okay, clear, everyone? Right, so I will write with the red one because it is not visible in white. Crank is fixed. Okay, crank is fixed. Now this is what we are having as a slotted bar. Okay, this is what we are having as a slider. Now you will say, sir, slotted bar is there, slider is there, connecting rod is there, crank is fixed. So connecting rod is acting as a driving crank, that is correct part. So it is what moving, complete rotation will be there for this connecting rod. And what other link is having the complete rotation? Because in the initially I have told you that rotation to rotation will be there. This slotted bar will be under complete rotation. Now in this case it will not oscillate. Earlier in the crank slotted bar it is what? Oscillating. But now in this case it will not oscillate. Okay, everyone? So this is the point you should remember. Now next, see, this kind of mechanism you will see obviously in the gate booster and the previous session also we have discussed the animation also. From that only we'll have taken the okay, snapshot I have taken here. Now these are the two extreme cases. This is the case before the cutting operation, this is the case after just the cutting has been what ended. So beginning of the cutting operation, end of the cutting operation. This point you should understand first of all. Beginning of cutting operation, at the end of cutting operation. Okay, so we can write here. Beginning of cutting stroke, okay, end of cutting stroke. Okay, everyone. Now see. Okay. So this point you should remember, the beginning of cutting stroke, end of the cutting stroke. Now how you will draw the extreme position diagram, combined extreme position diagram. Okay, you can draw like this. This is the crank which is what fixed. You can make such triangle here. Okay. So this is the crank which is fixed. Now see from the diagram here itself. So this blue member is the connecting rod which is acting as a driving crank. Okay. So at the beginning of the cutting operation it is like this, at the cutting of operation, at the end of the cutting operation it is like this. So obviously a triangle formation is there if I combine both the diagrams. If I combine both the diagrams, a triangle formation will be there. Okay, everyone. Now see. So same diagram you will see. Now in this case you should understand, okay, this is a connecting rod which is acting as a driving crank. Okay, this is the connecting rod. This is the crank we are having. Now you should understand which angle will be called as the cutting angle, right? So beginning of the cutting operation and end of the cutting operation. So obviously it has moved like this from here to here. Okay, better I will use a red color here. It has moved from here to here. Okay, from here to here it has moved. So this will be acting as a alpha, that is the cutting angle here, right? So obviously this will be the return stroke angle and we can say this is beta by 2. Clear, everyone? So QRR is nothing but the alpha by beta we are having. Okay. Now how you will calculate beta here in this case? See, angle opposite to will be the side opposite to angle will be the perpendicular here. This will be the base. Okay. So again in this case also you will use cos beta by 2. Okay. Base upon hypotenuse. Base will be the crank radius. Divided by the hypotenuse is what? Connecting rod. So I hope this cos beta by 2, this trigonometric relation you can directly use. This trigonometric relation you can directly use and you can calculate beta. If beta is calculated, alpha you can easily calculate, right? Just by using alpha plus beta equals to 360 degree. Okay, I hope this is clear. Now moving forward here, everyone please try to focus here and see. We'll come to this velocity analysis directly. Numerical they have asked from the velocity analysis, but in order to solve the numericals you should know the two different approaches. Both the approaches are equally important. We cannot say this one is good, this one is bad, or this one is what more advantages as compared to this one. Both are equally important according to the situations, right? Both are equally important. So first we'll discuss the relative velocity method, then icenter method. Both will discuss in a quick manner. We will discuss both the things. So first we'll take an example of 4-bar mechanism. Okay, we'll discuss the case of 4-bar mechanism, right, everyone? So this is a case of 4-bar mechanism. This is the turning pairs we are having. So let's suppose this link is what? Fixed. This A mentioning the name of the turning pair A, B, C, D. Now, what is the step number 1? Please quickly understand this point, very important. What is the step number 1? Identify the fixed points A and D. A, comma D are the fixed points. Okay. Now, let's suppose in the question itself they have given the angular velocity omega for link AB. So now, if angular velocity is given, we can easily calculate the velocity. How you can calculate? See everyone. Okay, everyone please see. Tangential velocity will be perpendicular to link AB. This will be velocity of B with respect to A, because you are observing the point B from point A. So this velocity vector just you have to draw. Okay. So this is point B we are having. Clear everyone? So direction you have to take care, right? Same direction you have to take care. Now what about point C? See, point C, again, observing the point C from point B, this can be the velocity vector, or velocity of C with respect to B, and you can have like this, velocity of C with respect to B. I don't know at this moment which direction will be the correct, so I will just make sure that this direction will be there like this. Okay. So this direction we will make sure here. Okay, right now at this moment I don't know where will be the direction of velocity of C with respect to B. Now consider the point C with respect to D. Consider the point C with respect to D. You will have the velocity vector like this. In both the direction it can be possible, right? Again we will use the same direction here. Now here you are observing the point C with respect to D, so you will draw the vector from point D. Earlier we have observed the point C from point B, so that's why we have used the point B here. Now I am observing point C from point D, so I will draw this vector from point D. So this direction you have to take. So now it is what intersecting here, so this point will be C. Okay, so try to understand, this is nothing but the velocity of B with respect to A, velocity of C with respect to D, and this is what velocity of C with respect to B. So this is the velocity diagram that you need to draw in order to solve the velocity analysis question. Okay, so such kind of velocity diagrams you need to draw. So this is the fundamental steps that you need to follow in order to draw velocity diagram. Step number 1, identify the fixed points A and D. In this case fixed points are there. Okay, we have shown the fixed points here. Second, whatever the angular velocity is given for any link, for that link you have to calculate the velocity. Okay, and easily you can identify the point because the magnitude is clear, no? So we can draw the length because the magnitude is clear, so we can draw the length of the vector also. So for velocity of B with respect to A, we have drawn up to this point because for that we have calculated the magnitude. Okay everyone, and see what will be the magnitude here. Velocity of B with respect to A will be nothing but AB multiplied by omega. Simple, as simple as. Okay, now clear? So this is the velocity diagram. Then velocity of C, you have to see, you have to observe the point C with respect to B and as well as with respect to D. So when you are observing from point B, this velocity vector will be there and this velocity vector perpendicular to BC will be there. Take this velocity vector, draw from point B because you are observing the point C from point B. Now you are observing point C with respect to point D. Draw the vector which is perpendicular to CD like this and take this vector and draw with respect from point D because as you are observing the point C from point D. Clear? So this velocity diagram you will get. Yes or no? Okay, now we'll move forward here. Now in this case what will happen? In the case of single slider crank mechanism, again same procedure you will follow here. Quickly everyone, please try and tell me whether you are getting the correct velocity diagram or not for this single slider crank mechanism. Everyone please try and tell whether you are getting the correct velocity diagram or not. Okay. Now everyone should try on your copy also, right? You have the copy, make a note of all the important formulas or the important relations that we are discussing, because you can have those relations in your examination also, you can use them, right? So this will be the revision only when you are having the copy and you are writing all the important formulas, right? So be attentive and try to remember, try to revise all those important formulas and the concepts here, right? Now see, try to observe. So let's suppose again I will first of all name the points here. Point A, B, C, and this is D. Now again, step number 1, fixed points. So the fixed points are A comma D. A comma D are the fixed points. Okay. Now let's suppose angular velocity is given for B like this. So obviously you will have what? The velocity of B with respect to A. AB into omega like this. Like this it will be there. So perpendicular to link AB, you have to draw the velocity vector. Okay, I will use red color here. Okay, I will make it right here like this. Velocity of B with respect to A. So same magnitude and direction you have to draw here. Okay. So let's suppose this is the point B you are having. Okay. Now observe the point C. Observe the point C with respect to B. So obviously perpendicular to link BC, you will have this kind of velocity vectors. Velocity of C with respect to B, velocity of C with respect to B. Same direction you have to follow here. Okay. So I will follow the same direction here as it is. Okay. Now observe the point C with respect to D. Now from the diagram itself, if you focus, you will see C point is what translating with respect to point D. Is this point clear? Yes or no? Point C that is on the slider itself is moving, or we can say directly it is having a translation motion. Okay, what kind of motion it is having? The translation motion with respect to the cylinder, because the point D is on the cylinder. So obviously what will be the direction of velocity vector? Horizontal. Like this the velocity vector will be there. So I will use the point D and I will draw like this. So this point we will get as point C. So now understand. So here this is velocity of B with respect to A, velocity of C with respect to B. This is what the velocity of C with respect to D, like this. This is the velocity vector you will get for the single slider crank mechanism. Okay everyone, the procedure is clear. So you can use this procedure for any kind of numerical, right? Any kind of numerical you can use such kind of procedure in order to get the velocity diagrams, right? Now next, eye-center method. In the case of eye-center method, you should understand first of all the concept behind eye-center also. Then there is one theorem, angular velocity ratio theorem, that you need to understand. Very important. Okay everyone, now see. So first we'll discuss this eye-center method. Okay, but before that you should understand, you should have some basic knowledge, okay, about this eye-center, right? So actually what happens, no, let's suppose this is the pin joint or the hinge joint and this is the rod you are having. Okay, so this is the point A you are having and here the point O is there. Now if you observe the point A from O, what you will have? The kind of rotation, right? So I can write velocity of A with respect to O as OA into omega, like this you can write. Now using this concept only, we will use this concept of eye center here, using this concept, right? How? Actually eye center is nothing but the unique reference point you have selected in such a way that it is nothing but the point of rotation for the body at that particular moment, right? So see, first of all you should understand the relative velocity method concept here. See, if I have to write the velocity of point B, let's suppose if I know the velocity of point A, so I can use this method, velocity of B with respect to A. So this is the relative concept, relative velocity concept. Let's suppose if you know the velocity of A and you want to calculate the velocity of B, A and B are the 2 points on the body itself, right? A and B are the 2 points on the body itself, or at anywhere you can consider. If you know the velocity of A, then you can calculate the velocity of B just by observing the B point from point A, and point A you know the velocity, right? So such velocity vector you will use and you will get the velocity of B. Now you have selected the reference point A in such a way that it is nothing but the point of rotation. So if it is a point of rotation, in that case it will not have the velocity. It will not have the velocity. So directly you will say you are having velocity of B as velocity of B with respect to A, and A is nothing but the point of rotation or center of rotation. You will write like this. Clear? So that is what the concept behind your I center, right? So I center is nothing but the unique reference point that you have selected in such a way that that point will be acting as a center of rotation for the body for any particular moment, right? For any particular moment you can consider any point. Okay, you have to consider a point about which body is assumed to be rotating. Actually in the real case it is not rotating, but for the moment we can assume body is what rotating about that point. So the sole purpose here is to first identify or locate your I center. If you are able to do that, you can easily use the concept of I center, like angular velocity ratio theorem, right? Now I will quickly tell you some important points here, right? How you will calculate. So let's suppose first of all what should you remember here? First of all, let's suppose this is a body here. Point A is there, point B is there. Okay. Now consider this point. For point B, they have given you this is the velocity vector, like this they have given you, and for A it is like this. For A, let's suppose it is like this, the velocity of point A. Okay, like this it is there. Clear, everyone? Now what you have to do here in this case, for example, such kind of system they have given, and there you have to identify you have to locate what? The I center. What you will do here? You will do what? Draw the perpendicular line from the velocity vector. Okay, just draw the line perpendicular to the velocity vector, everyone. Okay, perpendicular to the velocity vector you will draw. Okay, like this you will draw. So wherever they are meeting, that point will be what? I center. Perpendicular to the velocity vector you will draw the lines, and wherever the lines are crossing or intersecting, that point will be known as the I center. Clear? So in order to identify the I center, what you will do? Draw the line perpendicular to the velocity vector. Okay, if for 2 points, if you know the velocity vector, just draw the perpendicular lines. One more example, from which obviously in the GATE examination they have asked question. I will take that example only, right? So let's suppose this is what you are having as a slide ladder here, AB, and obviously see, for this ladder, if let's suppose it is sliding, so velocity of A will be like this and velocity of B will be like this. Obvious, pretty much obvious thing. What you will do? You will draw the velocity vector you will draw the line which is perpendicular to the velocity vector. It will be like this. Okay, just a point here. The velocity vector. Okay, considering the velocity vector, draw a line perpendicular to the velocity vector. So wherever they are intersecting, that point will be I center. Perpendicular to the velocity vector, you have to draw the line. Wherever the lines are intersecting, that point is nothing but the I center itself. Okay, I hope this point is clear. Now coming to this angular velocity ratio theorem, please, this is one of the most important theorem in order to solve any numerical with regards to simple mechanism in which they are asking the velocities, right? What we will do here in this case, see first. So I will take an example of 4-bar mechanism here. Right, see. Now, so let's suppose this is we are having link 1, link 2, link 3 and link 4. So first of all, you should understand where are the I centers here in this case. So this I center will be I12, I14, okay, and this will be I23 and this will be I34. Like this, you will have the eye centers. But how you will identify the eye center 2, 4 and 1, 3? Quickly tell me which property, which relation you will use here in order to identify the eye center I13 and 23. Tell me fast, guys. Okay, now I will tell you how you will find out the eye center 1, 3 and 2, 4, right? So simply you have to draw a circle like this. In this circle, see, you will have 4 points here. From that points, you will draw the triangle here. So this is the point 1, point 2, point 3 and point 4. In order to identify or locate the position of eye center 2, 4, see what you will do, you will go from 2 to 4. So in order to go from I24, if you want to go from 2 to 4, what are the two different ways? Go from 2 to 1 and 1 to 4. I can write 1 to 2 and 1, 4. Another way will be what? 2 to 3 and 3 to 4. Now you should draw the line 1, 2 and 1, 4. A line consisting of I12 and I14. Okay, I will draw a line here consisting of 1, 2 and 1, 4. Another line consisting of 2, 3 and 3, 4. 2, 3 and 3, 4. Another line consisting of 2, 3 and 3, 4. This is 2, 3. So here it is meeting. This is my I24. Right? Now what about 1, 3? What about 1, 3? Everyone, guys, please tell me. What about 1, 3? In order to go from 1 to 3, what you will do here? Okay, simply you will say, sir, from going 1 to 3, I can use two different ways, 1 to 2 and 2 to 3, and I can use 1, 4 and 3, 4. Right. So 1, 2 and 2, 3. What are 1, 2 and 2, 3? This points. So just draw the line. Another line 1, 4 and 3, 4. 1, 4 and 3, 4. Just extend this line. Here these points are meeting. So this is I13. I hope the location, how to identify the location of different eye center for a case of 4-bar mechanism, it is clear to everybody, right? Now we will use the angular velocity ratio theorem. Till now, any doubts? Guys, please tell me, is there any doubt? Clear? Now see, for the angular velocity ratio theorem, I am taking I24 or I13. It's your choice. Okay. Now see, considering I24 or considering, let's suppose I24, first of all, I will take I24. After that, I will take I13 also, no problem. I24. See, I24 is there, I center. I can consider I24 as I center for the link 2 also, for link 4 also, right? Now, how you will do? How you will apply this particular angular velocity ratio theorem? See, you will write like this: omega 2 by omega 4 equals to I24 I14 I24 I12, right? Actually, it is nothing but like this: omega 2 multiplied by distance from I24 to I12, distance of I24 from I12 equals to omega 4 multiplied by the distance I24 from distance of I24 from I14, like this it is there. Okay, I hope this point is clear. Now considering the next case, I13. Let's suppose for that matter, I will take this one. The next case, I23. For example, I will use I23. Okay, I23. How I'll use here I23? See, I will write omega 2 divided by omega 3, and it will be equals to, common eye center is I23, distance of I23 from, see, inverse ratio is there. So I will use I13 here, and again distance of I23 from I12. This relation I will use. Clear? This relation I will use. So see, depending upon the eye center, you can use this relation, angular velocity ratio theorem. Okay, you will consider one of the link. Okay, you have to consider one of the link as the reference link here. You have to consider one of the link as the reference link here. Right? Is this point clear? So 2,4 we can write like this. For 2,3 we can write like this. Clear, everyone? Okay, is this point clear? How to write the angular velocity ratio theorem in this case? So consider any eye center. Let's suppose 2,3, 2,4, any eye center you can consider. Omega 2 by omega 3 is there here, but in this case the inverse ratio will come. Distance of I23, common eye center, that is what common eye center, distance of common eye center from I13. Distance of common eye center I23 from I12. You will take like this. Because here 2 is there, so I12 here. Omega 3 is there, omega I13 will be there like this. Omega 4 is there, omega I14 is there. Omega 2, I12. Like this, it will be there. So I will consider the fixed link as a reference link, right? Are you getting the point? I14, I12, I13, I12. I have considered the link 1 as the reference link, which is what the fixed link here. That's why I have taken the link 1 as the reference link here. Clear, everyone? I hope this point is also clear. Now, moving forward here. Analysis of slider crank mechanism, right? What kind of questions they can frame from the single slider crank mechanism? Like what is the velocity? What is the acceleration? What is the torque requirement? Okay, what is the torque requirement? Like that they can ask. Okay, now see, everyone please try to understand in this case what will happen. If I have to calculate the velocity of slider, okay, it will be nothing but r into omega. This formula everyone should remember, sin theta plus sin 2 theta divided by 2n. That is what the approximate formula. But actually what mistakes a student will do here, they will forget some important basic terminologies regarding this slider crank mechanism. What are these? See, first of all, stroke. If I talk about stroke, because in the question they will give you stroke, and a stroke will be nothing but the twice of crank radius. Clear, everyone? What is n here? It is the ratio of length of connecting rod divided by the crank radius. Clear? Stroke is the twice of crank radius, and that is what the ratio of length of connecting rod divided by the crank radius. So generally they will give the stroke. They will give stroke length. Actually this is the stroke length twice of crank radius. They will give the displacement of the slider as the percentage of stroke, like 25% of the stroke. The piston has displaced whatever the displacement of the piston is there, it is equals to 25% of the stroke length. So what is the stroke length? Twice of crank radius. So 25% of 2r will be what? You have to take 1 by 4 of 2r, right? Like this you have to calculate. Clear, everyone? Is this point clear? Yes or no? Please tell me fast. Is this point clear? Okay, so these points are what very important, guys, that you should remember. Okay, so velocity of the slider is this one. Now if I talk about this point, acceleration of slider, it is nothing but the r into omega square cos theta. Okay, don't write this sign here, it is the cos theta here. Okay, cos theta cos 2 theta divided by n. Okay, actually in this case 2 will not come. So these are the two important formulas that everyone should remember. These are the two formulas that everyone should remember. Yes or no, guys? Velocity of slider, acceleration of the slider, right? Is this point clear? So these kinematic analysis point you should remember. Okay, now what about the dynamic analysis? First, in the kinematic we will discuss velocity and acceleration only. In the case of dynamic we will discuss the forces that will be what applied on the various links here in this case. Okay, just a minute. We'll take the diagram here. Okay, we'll draw the diagram. Actually the diagram is not there, so we'll draw the diagram here. See, this is the slider we are having, connecting rod, crank, okay, Clear everyone? Is this point clear? Yes or no? Okay, now see, try to understand this point, very important. See, some net force will be acting on the piston. Some net force will be acting on the piston. That point is known as the piston effort. So some net force is acting. So we'll call piston effort. Okay. Now how the connecting rod is connected? Like this. So obviously some connecting rod force will be acting here. Okay. So there will be one normal also. That will be because the piston is having, or the slider is having the contact with the cylinder. So definitely some normal force will be there. But in order to write this connecting force here, I can use this simple basic concept here, that Fp will be equals to Fc cos beta. Actually this angle I will take it as beta here, and I will take this angle as a theta here. Okay. So Fc cos beta, and if you have to calculate this Fc, it will be Fp divided by cos beta. Like this you will do here. Okay, like this. Now if I consider this point here, okay, this point if I consider, okay, so I will draw here. Okay, try to understand this point. Okay, now see. So obviously along the connecting rod force will be there. Okay, along the connecting rod. But there will be one force here. Okay, there will be one force which is perpendicular to this crank. Okay, perpendicular to the crank. So we'll take this line here. Not perpendicular, we will take here first of all, like this. Okay, now it is like this. Now see. Okay, now see. So along this connecting rod, this Fc force will be there, right? But this is a crank. Perpendicular force to the crank we have to calculate, so that we can calculate the torque, right? That is the point you should understand. Perpendicular to the crank will be known as the Ft, the crank effort, right? So obviously this angle first we have called this as beta. So here this will be beta, this will be theta, as this angle is what? Theta here. Okay everyone. Now what will be Ft here? Ft will be Fc sine theta plus beta, right, like this. So what is the Ft? Ft is the force perpendicular to the crank. Now in order to calculate the torque, just multiply the Ft force with the crank radius, and after that they can also calculate, they can also ask the power, that is, or torque multiplied by omega, right? Is this point clear everyone? So like this you can also do the dynamic analysis. There is no need to remember any formula in the case of dynamic analysis. Just remember the diagram, how the force we have considered, okay, in each and every member of the slider crank mechanism. Okay, that point you should remember. Okay everyone. Now moving to the next topic. Guys, is this point clear? Up to this point everything is clear, yes or no? Please tell me fast. Okay, now we'll start the next topic here, that is the flywheel. Okay, we'll start the next topic, flywheel here, right? Now in the flywheel, first of all you should understand what is the work done per cycle. Very important formula guys, very important. So actually this is the diagram for the four-stroke engine. Okay, so this is the torque we are having in the y-axis, in the x-axis the theta, the crank rotation, right? What is this dotted line? Mean torque. Now actually if there is no flywheel, such kind of variation of the torque you will see with respect to the crank rotation. Now if such kind of fluctuation is there actually in our engine, so what will happen? We will not able to properly ride a vehicle. Okay, you cannot run the vehicle with such kind of fluctuations. It is impossible, next to impossible to run the vehicle with such kind of fluctuation in the torque value, right? So what we have to do, we have to reduce such fluctuations. For that we are using the flywheel only. And what is this mean torque? Mean torque is the torque which is what just required to run the engine. Okay, now let's suppose if you want to accelerate your vehicle, obviously the torque has to be what? More than the mean torque. Clear? So first of all, you should understand such kind of variation is there. And if I talk about the variation part, see, this part is what we are having as a suction. Here we'll have a compression. Here we'll have expansion. Here we will have exhaust. Right? Exhaust, expansion, compression, suction, like this. Now most of the work that you will get from the engine is during the expansion only. You will get the work during the expansion only, but that much amount of work is actually more than the required. So what we have to do? We have to store the extra amount of energy that the engine has produced. Okay, for that we'll use what? Flywheel only. Flywheel will store the excess amount of energy and it will return it back during the time at which we are what? Energy deficient. In that time the flywheel will return back the energy. Clear everyone? So this is the point first of all you should understand. Now how to calculate the work done per cycle? Right, now we'll write down the formulas here. See, first formula, work done per cycle. See, integration of T d theta, 0 to theta, but theta will be here time period, this theta. Okay, we have to call this theta as time period. Okay, you can remove this one. Right, this is the point. 0 to time period T d theta you have to integrate. Clear? Now you can also write work done per cycle as mean torque into time theta. Again, theta is what? The time period. So both these values will be equal. So from equation 1 and 2, if you have to calculate mean torque, we can use both the equation 1 and 2. Mean torque will be equals to what? Integration 0 to theta d theta divided by time period. This formula you can utilize here in order to calculate the mean torque. Yes everyone, please tell me, this is clear, yes or no? Yes everyone. So simply the mean torque will be nothing but the work done per cycle divided by the time period. So this formula is very important. Most of the time they will be asking the mean torque, and you have to check whether the actual torque is greater than the mean torque or not. If it is greater than the mean torque, obviously body will accelerate, the engine will accelerate actually, and if it is less than mean torque, it will retardation will be there, deacceleration will be there. Okay, now see, I have the points are clear. Now important parameters in the flywheel that we should remember, okay, because in the question language they will give such important informations like coefficient of fluctuation of speed, or somewhat in some cases also they can ask directly, okay, but you should remember the importance of each and every term here. Okay, so coefficient of fluctuation of speed, if I say, they have used the coefficient CS notation, actually CS they will use here. Now in order to calculate CS, the formula that we have to use is what? C, omega max minus omega minimum divided by omega average. Clear everyone, yes or no? Right, in the similar way coefficient of energy also they will ask. In a similar way also they will ask the coefficient of fluctuation of energy. In terms of omega also you can write, in terms of RPM you can also write, right? So it will be like this, N average. Okay, this is the formula for the CS. Now what about the coefficient of fluctuation of energy? See, this is CE we will write. Here the CE formula will be E max, E minimum divided by E average. Now you should understand how to calculate E max, E minimum. See, E will be nothing but the kinetic energy, half I omega square. Okay, half I omega, I is the mass amount of inertia, right? Now, if the omega is maximum, E max will be there. Omega minimum, obviously E minimum you will have. For the E average, omega average you have to put. Clear? Now, most importantly, the fluctuation of energy, right? The delta E formula actually, it is equals to I omega square CS. I omega square CS is the formula that you should remember. Most of the numericals are based on this formula only. These are the supporting parameters. Most importantly, they will be asking delta E, the fluctuation of energy, I omega square CS. Okay, everyone? Now, here in this case, omega is what the average omega, right? Remember this point. Average omega is there. And even you can also calculate delta E as what? E max minus E minimum. Clear? Yes or no? Okay. Now, see. Now, next topic, gate train. Okay. Next topic is the gate train. Very important. Definitely, they will be asking a question from the gate train. And if I to be very specific in the gate train, epicyclic gate train is the topic from which they will be definitely asking a numerical. If you observe the PYQ trend, no. If you observe the PYQ trend, this gate train, from this gate train, actually epicyclic gate train is the part from which they will be asking question. Okay. Repeatedly they have asked the question from the gate train itself. Epicyclic gate train, right? But in order to revise some important points, I have mentioned the points here, like simple gate train. Simple gate train, in the, what will happen in the simple gate train? Each shaft will carry one gear. Each shaft will carry one gear, right? Simple point. Next, there is a purpose of idler gear. Actually, in the simple gate train, the intermediate gears are known as the idler gear. Remember this point. This is what the intermediate gear. Okay, so what is the purpose of intermediate gear? And actually, we will call intermediate gear as the idler gear. Okay, to connect the gears where the large distance is required, obviously, to control the directional relationship between the gears. And how they will control, check. See, obviously there will not be any influence on the velocity ratio, but if the number of idler gears are even, direction will be opposite. Okay. If the number of idler gears are odd, direction will be same. See, in this case, 1, okay, you can consider it as the odd here. So let's suppose it is clockwise, it will be anti-clockwise, but it will again clockwise. So direction of input and output is what? Same. So that is what written here. Odd number of idler gear, direction same. Even number of idler gear, direction opposite. That point you should remember. Now, compound gate train. What will happen in the compound gate train, guys? In the compound gate train, remember this point. In the case of compound gate train, one of the shaft will have gears. More than one gear will have. One of the shaft will have more than one gear. Now, whatever the gears the shaft is carrying, all will have the same speed of rotation. Let's suppose one of the shaft is carrying 2 gears. So for both the gears, speed of rotation will be same. Is this point clear? Very simple point, right? So whenever shaft is having more than one gear, the speed of rotation will be same. So if, let's suppose simple gate train is there, so what will happen in the simple gate train? Each shaft having same only one gear. Now in the compound gate train, one of the shaft will have more than one gear, right? So that is the possibility here. So let's suppose this is the input gear, this is the output gear, and this intermediate gear, one of the intermediate shaft will have more than one gear, right? This point you should remember. So this is the front view you can have, this is one of the view you can have, and this is the another view, right? So this shaft is carrying this gear also. Let's suppose this is gear number 1, gear number 2, gear number 3, and gear number 4. So from this you can say, sir, omega 3 will be equals to omega 4, right? This point you can easily mention here. Okay, correct everyone? So omega 2 equals to omega 3 will be there, and omega 1, see, for the gear 1 is the input gear, gear 4 is the output gear. Intermediate shaft is having more than one gears. Now next, reverted gate train. So what is the unique point in the reverted gate train? That the input shaft and output shaft are collinear. See, gear 1, gear 2, gear 3, gear 4. You can consider gear 1 as the input gear. Input gear, or even you can consider it as a driver. Actually, you can consider it as a driver here, and gear 4 as the driven gear. Right, now please remember this point. So actually the gear 1, that is the input or the driver gear, is having an axis like this, which is what common with the output, which is what the common with the output gear. So, or the driven gear actually. So whenever the driver and the driven gears main, actually you should write here the main driver, otherwise you will have a confusion. Main driver and the main driven will have a common axis. So that kind of a gate train will be the reverted gate train. Next, epicyclic gate train. Next, epicyclic gate train, guys. From this gate train only you will have the numerical. Okay, if they will ask the question from the compound gate train, simple gate train, or even in that matter reverted gate train, those numericals are what very easy. But epicyclic gate train is one of the most important topic as far as the gate numerical is concerned. You can check the PYQ also. Okay, based on the PYQ only I am telling that this is the most important topic. So what will happen in this case? See, in epicyclic gate train, axis of the gear will rotate about the axis of other wheel in addition to the revolution around their respective axis. Like this gear will rotate about its own axis as well as it is rotating about the bigger gear. Are you getting the point? This blue one gear is rotating about its own axis, and as well as in addition to that it is rotating about the gear C, the gear green, the green gear actually, the bigger gear, about that also it is rotating. So 2 degree of freedom you will consider here, 2 degree of freedom you can consider here. Okay everyone, now I hope the point is clear. Now see, in order to solve this epicyclic gate train problems, 2 methods we have discussed in the class, but one of the most important method, or I will say the best method, is what the relative velocity method. You can use the relative velocity method and it will solve the numerical in very much less time, right? And you can save the time also. So what is the concept behind this relative velocity method? I will discuss it in a very quick manner here. So for example, if I give you some example here, let's suppose this is the gear you are having. Okay, and let's suppose, okay, so let's suppose this is the sun gear. Okay, sorry, it will, let's suppose if I consider this one as a ring gear, not the sun gear. So this is the ring gear. Okay, this is the planet gear, and let's suppose this is the sun gear. Okay, like this, and this is what the arm. So different velocities, different cases they will give you. Okay, now you should understand this point that they can ask any parameter with regards to planet gear, arm gear, or the ring gear, anything they can ask. But what should you consider here? Okay, which relations you will use here? Okay, I will tell you here. So any simple, any case I have taken, okay, assume that the number of teeth is known or one of the velocities they will ask. Okay, and they will definitely give some velocity as well, but definitely, so they can ask, see, they can ask the planet gear also, arm also, sun and the ring, whatever they can ask, but for that they will give at least some velocities of other gear also, right? So let's suppose I am assuming the ring gear to be what? Fixed. So this notation shows what? It represents what? The ring gear is fixed, right? Okay, so now consider this point very carefully. Okay, so when I will write here the velocity of planet gear, okay, See, when I say relative velocity, you are considering any particular gear with respect to any other gear. Okay, so you can consider any gear. For reference, you can consider any gear. But see, as far as the epicyclic gate train is concerned, I will take the reference of arm. I will take the reference of arm. Right, so omega of planet gear with respect to arm I will take. So what it will be? It will be nothing but omega p minus omega arm. Right. So like that I can write. So even I can write omega of sun gear with respect to arm. It will be omega sun minus omega arm. Right? Clear everyone? Is this point clear? Right. So actually this is a gate train, not a transformer, Ankit. So this two equations you should understand. Okay. So if I have to write, let's suppose for that matter also ring gear, we can write omega r minus omega arm. Right. So I can select any particular gear. Now let's suppose, see, you have to consider the gearings first of all. Planet and the sun will have external gearing, but planet and the ring will have what? Internal gearing. So let's suppose I am considering the gearing of planet and sun gear. Okay, so I can write omega p with respect to arm divided by omega of sun gear with respect to arm. So this ratio will be equals to Ts divided by Tp. But a negative sign will be there. Why? Because the external meshing is there. Right? Like this. So with respect to arm we are writing. So this is the relation that we'll use here. Now planet and the ring gear is also having the meshing, but internal meshing is there. So how we will write here? See, we can write here omega of ring with respect to arm divided by omega of planet with respect to arm equals to Tp by Tr with a positive sign here. So these relations we can use here. Okay, this kind of a relative velocity concept method we can use here in order to solve any parameter whatever they have asked. This will take a very less time also and quickly you can solve. Okay everyone. Okay, and obviously you will save some time, no? If you save some time, definitely you will utilize that time in some another questions in which actually the time requirement is what? More. Okay, some lengthy numericals will be there in the examination, right? So see, out of 65, definitely 4 to 5 question will be what? Tough. I can say, let's suppose even 10 to 15 question is tough. But the remaining question you should target, right? But the remaining question you should target. So out of that, how much correct you are doing, it is the thing that you have to work on, and you have to improve the efficiency also. Let's suppose you are attempting 50 question. Out of 50, I can say 2 to 3 or 4 question will be wrong. But you have to improve your efficiency, right? More than 95% efficiency you should have. It is not like that. Let's suppose you have attempted all 65 and out of 65, 50% questions you have done as wrong. So then there will not be any use here. You have to increase the number of questions also, and as well as you have to solve the question correctly. You have to increase the efficiency also. Okay. Now I hope the concept is clear regarding the epicyclic gate train. Next thing, the governor. So governor is one of the most important part, guys. We'll discuss one by one different governors. Okay, so first the Watt governor. Tell me the formula for the calculation of the speed of rotation here. Everyone please tell me the formula for the speed of rotation for the Watt governor case. See, it is one of the most basic form of the governor, guys. One of the basic form of the governor, okay, and very easy also. Right, so actually here you should understand the height of governor. You can mention the height of governor equals to 895 by n square. This formula you should remember. For the Watt governor, remember this point. Okay, so this will be the diagram here. This is what we are having is the height of governor. This is the radius of rotation, right? So whatever the height of governor they have given, okay, for that you can calculate the speed of rotation, or even you can calculate the height of governor for the whatever the speed of rotation they have given. Clear? So H equals to 895 by n square will be the formula for the Watt governor. Clear? And actually you should understand one more important point here, why we are not using this Watt governor. Because see what will happen, as the speed of rotation increases, see, if you put the value, see, you can check yourself also, if you increase the speed of rotation, what will happen to the value of H? The H value will be what? Very less. It becomes so less that, see, H value becomes like 0.09 mm. Okay, so see, 0.9 movement of the see, actually for one speed of rotation, let's suppose, for example, I will give you, for n1 there will be what? H1 height. For n2 there will be what? H2 height. Now if these speeds are what? Very high, obviously in that case this H1 and H2 will be what? Very less, and if I take the difference, that value will become very less. So H1 minus H2 will be what? The movement of the sleeve. H1 minus H2 will be nothing but the movement of sleeve, and if the movement of the sleeve is what? Very less, okay, how you will regulate the fuel supply? Okay, so actually we will regulate the fuel supply based on the movement of the sleeve. If the sleeve is not moving, okay, so how you can regulate the fuel flow? Okay, we cannot regulate, right? So fuel flow, the regulation of the fuel flow will depend upon the movement of the sleeve, right? At least it has to move, then only the every mechanism will work. Okay, so this point you should remember. Clear? So next governor is the Porter governor. So that's why the Watt governor not be utilized for the high speed application. For the low speed application it is good, but for high speed application it is not good here. Okay, that is the point. Next is the Porter governor. What difference we are having in the Porter governor? We have attached some mass on the sleeve. Okay, we have attached some mass on the sleeve. Now what is the difference, right? So by attaching that mass on the sleeve, what advantage we are getting? Anyone please tell me what advantage we are getting by putting the mass on the sleeve? Okay, what advantage you will get? Tell me everyone. So in a meanwhile I will write the formula here. See, H equals to 895 by n square brackets small mg plus minus capital Mg. Okay, here it will be plus capital Mg plus minus the frictional force divided by 2, 1 plus K small mg. So this is the formula, guys, that you should remember, everyone. Now everyone should understand what is K here. Okay, what is K here? First of all, what is K here, that you should understand. What is F force here, that you should understand. What is small m here? What is the capital M here? Now what is the value of K here? Anyone? What is the value of K here? Okay, so see, I hope the diagram is what clear. This angle, see, I will mention here with the different color so that it is easily visible to you. This angle I am talking alpha, this angle I am talking beta, right? Okay, this angle is alpha, this is beta here. This is the centrifugal force that will act on the mass of the or the fly ball, I can say. Okay, this capital M is the mass that is what placed on the sleeve, right? This is alpha, this is what beta. This is what beta, alpha, beta, like this. Correct, everyone? Okay, is this point clear, everyone? So see, actually F is nothing but the frictional force we are having. Clear? F is the frictional force. Okay, okay, but before that we should write K, that is 10 beta divided by 10 alpha frictional force, right? Small m, mass of fly ball, or simply mass of ball, you can say. Mass attached to sleeve. Mass attached to sleeve, right? Like this. So this is the K value, K, 10 beta by alpha. You have to check whether beta and alpha is or not there. Himanshi is not clear, please. Which part is not clear? I think the diagram is not clear. Please tell me which part is not clear, right? So this formula, H is what the height of the governor, which is equals to 895 by n square, and this formula that you need to remember in the case of Porter governor. These are the parameters that has been what used in this formula, where K is 10 beta by 10 alpha. Diagram part, see, first of all, you should understand the Porter governor part. Okay, here I will draw the diagram here again, so that you will have the idea. See, so some mass has been placed on the Porter governor. So difference between what and Porter governor is what? Some mass has been placed on the sleeve, right? So now during the analysis, I will consider the half part only. So what I will do here, see. So it is like this. This is the upper arm, lower arm, like this. Okay. So obviously it is having some angle here, alpha, and it is having some angle beta. Now you should understand this, this point and this point are not in the same line, right? So you should understand this point. Okay. Now see, here the force which will be acting here, mg by 2, okay, and here it is what mg it will be acting, and here the centrifugal force will be acting. Now if you consider the whole part here, the I center will be here. This is the point of I center. For moment, see, I will consider the moment. Yes, Himanshi, the offline classes are in the Bangalore also, in the Vijayawada also. You can contact with the team also, right? There is the number mentioned in the website also. You can directly contact with the team and they will guide you where you can take the admissions, right? So just consider this point. This is the I center about which we will take the moment, right? This is the point about which we will take the moments, right? And after solving, after deriving all those things, you will get the final formula, right? Today we are not going into the derivation part, anything, just it is a revision session. So we are focusing on the formula only, right? We are focusing on the formulas and the relations that you have to remember just before the GATE examination. So that's why we are focusing on the formula only. We will not discuss the entire derivation part here, but I've given you some basic idea, right? So this formula you need to remember, and see, F is the frictional force. But why I have written plus minus sign? See, when the sleeve is moving upwards, so friction force will acting downwards. When the sleeve is downward, moving downward, friction force will upward. So that's why we have used the plus minus sign. Okay, you have to consider this point, everyone. Okay. Now next point. So we have discussed this thing. Now Proel governor, right? Now Proel governor, everyone please see. Proel governor, again this angle is alpha, this angle is beta, right? This 10 alpha will be equals to R by H, right? Like this. Mg plus minus F divided by 2, it will be there. Now we will write the formula for the Proel governor. See, earlier we have already written the formula for the Proel governor. Okay, same formula will be there. Some small changes will be there. Only small changes. Can you tell me what are the small changes that you will see? See, I will write the same formula here. Okay, I will write down the formula, same formula. H value 895 by n square, small mg plus capital Mg plus minus friction force divided by 2 into 1 plus k, the whole denominator mg, right? Now you should tell me, this is the same formula that I have written here, same formula, only small changes we have to what implement in the formula for the provisional governor. That's how we can remember the formula, right? We don't have that much time in deriving the formulas, right? So we have to figure out the way in which we can remember the formula. So only small changes will be there. Can you tell me which will be what are those small changes? What are those small changes, guys? Okay, actually, see, here you will see AQ, distance AQ divided by PQ. This fraction you need to consider. Okay, now again, why this fraction is there? Why only AQ by PQ? Actually, through the derivation only it will come. But for the examination point of view, you have to remember the formula. See, in the diagram here, I hope it is visible to everybody, right? So in the diagram, if you see, this is the point Q we are having, this is the point A we are having, and this is the point P we are having. So actually what will happen in the provisional governor, there is the extension of the arms here. This is the extension of the arm. But if you observe the previous cases, there is no extension of the arm in the provisional as well as the what governor, right? But if you see in the what and the porter governor, no extension of the arms, but in the provisional governor, extension of the arm is there. So let's suppose we have considered the extension as vertical. So this upper point we have considered as a P, the bottommost point we have considered Q, and this point where the extension is there, that point is what? A. So like that you have to remember AQ is the lower part distance and PQ is the total distance, right? Like that you have to remember, because anyhow, see, if this question comes, you have to remember this formula and directly apply, right? Clear, everyone? So now if you see the formula, again this formula, if I remove AQ by PQ, you will get the porter governor formula, right? If I remove this complete bracket here, you will get what? The what governor formula? You will get what? The what governor formula. Clear? Is this point clear, everyone? Okay. Now see further. Hartnell governor. Actually, what will happen in the Hartnell governor, guys? In the Hartnell governor, what is the difference? It is the spring-loaded governor. Earlier, whatever governors we have discussed, those governors are what? Dead weight. Okay, some dead weight is there. Now in this case, the spring is there. Okay, spring controlled governor is there. Okay, Hartnell is the one of the spring controlled governor. So as the speed of rotation of this spindle is increases, the ball movement will be there high, and because of that this sleeve will be what? Move upwards, and there will be what? Compression in the spring, right? So in this what happens? No, two different cases will be there. Case 1 and case 2 I have mentioned here. Let's suppose, see, when the speed increases, so ball will have a much larger radius of rotation, and the speed decreases, the radius of rotation decreases. So obviously this case belongs to the maximum speed of rotation, this case belongs to the minimum speed of rotation, right? So I will mention here also, it is the case of maximum speed of rotation and this is the case of minimum speed of rotation. Clear, everyone? Okay, I hope this is clear. Now the horizontal arm I can consider as X, vertical arm as Y. Again, horizontal arm X, vertical Y, like this. So there will be what? A movement here. Okay, some theta angle. Okay, some theta angle movement will be there. Same angle theta will be there. So like this, like this. This is what you can consider H2 here. In this case you can consider H1. Clear, everyone? Now at this point everyone is clear up to this point, right? Okay, now I can easily write, see, there is a most important point that you should understand. I have to mention what? The radius of rotation also. So for that I will mention the spindle axis here. Here also I have to mention the spindle axis. Okay, so this is what we are having, this radius of rotation R. This radius of rotation is what? R2, right? Speed radius of rotation R, and this one is what? Radius of rotation R1. Clear, everyone? Right? Now see, from here also theta you can calculate, from here also theta you can calculate, but I need this H1. Okay, for that, let's suppose if I use this theta here. So this theta equals to perpendicular upon base. Perpendicular will be what? R1 minus R divided by base will be what? Y here. Clear? Yes or no? What about this one? In this case, it will be equals to perpendicular H1 divided by the base, that is what? X. So I can easily write here the value of H here. So actually why I am writing here, so that you will be able to understand how to calculate the lift. Here. Okay. So actually I will write here H1 value as what? X1 X by Y R1 minus R. And in this case directly I am writing H2. Okay, it will be again X by Y R minus R2. Now if I add H1 and H2, I will get what? I will get the displacement, or I will, better to say, the lift of the sleeve. Lift of the sleeve I will get. Are you getting the point? Lift of the sleeve I will get if I add this H1 value and H2 value. H1 and H2 value if I add, I will get what? The lift of the sleeve. Yes or no? So just you need to add H1 plus H2. X by Y will get R1 minus R2. So this is the formula for the lift of the sleeve. Clear everyone? So like that you should remember, it is nothing but the sleeve movement. Better to write instead of writing H1 plus H2, we should write this, only we will have to write H. This H value is what? The sleeve movement. This is what the sleeve movement. Clear? Okay, I hope this is clear. Now, if this is the sleeve movement, see what other parameters they can ask, like stiffness of the spring. Stiffness of the spring they will be asking. Most important parameter, the stiffness of the spring they will be asking, right everyone? Okay, stiffness of the spring, that formula is what? Very important, and everyone should remember that formula. Okay, stiffness of the spring. So let's suppose stiffness of the spring I will represent with S. So it is nothing but 2 into Y by X whole square FC1 minus FC2 divided by R1 minus R2. And what is this FC1? The centrifugal force only. It will be nothing but mR omega square, like this. So this formula, this is what? The stiffness of the spring. Stiffness of the spring. Yes everyone, please tell me first, is this clear? So 2 into Y by X whole square into FC1 minus FC2 divided by R1 minus R2. This formula is what? Very important in the case of governor, right? Okay, now next, this graph at least you should remember for the GATE examination. How to identify stable governor, unstable governor, or the isochronous governor. Actually this graph is for the spring control governors only, right? So if the line is like this, okay, if you observe here, the line is like this. Okay, I will use the different color. If it is like this, it is the unstable governor. If it is passing through the origin, isochronous, and if it is having like this, the stable governor. So definitely you can understand, this is the negative intercept, here the positive intercept. Negative intercept, stable governor. Positive intercept, the unstable governor. Okay, actually this spring control governors. Okay, so you should also remember the equation also. Unstable, FC equals to AR plus B. A and B are the constants value. FC the centrifugal force or the controlling force. R is the radius of rotation. For the stable one, it is AR equals to minus B, right, like this. So you have to remember the formulas also as well as, right. So lot of things are there behind this, the formation of this graph, but we don't need to discuss, we don't need to see those things right now at this moment, because only few days are left for the GATE examination. We have to be focus on the most important points, right? So this is one of the most important point, which line will be considered as stable, unstable, or isochronous, that directly I need to understand at this moment. Okay, but obviously in the classes also we are deriving everything, we are understanding everything, each and everything, but at this moment for the revision session we cannot discuss all those things, right? So just try to remember this diagram. Okay, now gyroscope, one of the most easiest topic I would say, right? Just you need to remember how to identify the direction of rotation, and there is one formula only, very simple. Okay, very simple case. Okay, very simple case is there. Just you need to know how to identify the direction of rotation. That is what required. Clear, everyone? Now tell me, is everything is clear? Okay, now we'll see how the gyroscopic couple we can discuss. So first, direction of rotation, right? See how we can identify the direction of rotation, everyone. So let's suppose there is the rotor here. There is a rotor here. Now let's suppose if you are observing this rotor from this side. Okay, now if you are observing the rotor from this side, right hand side, and this will be the left hand side, and they have mentioned that it is having anti-clockwise rotation. So this thing they will tell from the front or the right hand side it is anti-clockwise movement, or from the this side left hand side it is having the clockwise sense of rotation, obviously. So if I observe this one, if it is having anti-clockwise sense of rotation, obviously from this side it will be clockwise. So that is what the problem we are facing. If I say the rotation in terms of clock or anti-clock, so as we move on to the other frame, the sense of rotation changes. So that is one of the most important problem. So in order to avoid that situation, we will be using the vector. We will be using what? The direction of rotation in terms of vector. Not we will tell like clockwise sense of rotation or anti-clockwise sense of rotation. We will not tell like this. We will use the direction of rotation in terms of vector. For that, we have to use right hand thumb rule. Okay, now see. So what will happen? So they are saying that anti-clockwise sense of rotation is there. Just curl your fingers in the anti-clockwise sense. Just curl your fingers in the anti-clockwise sense, and the thumb will show what? The direction. Thumb will show what? The direction of rotation. Right? Is this point clear? Yes or no? So this will be the direction of rotation. This arrow will represent the direction of rotation. Direction of rotation. Clear, everyone? Direction of rotation in terms of vector, right? Using, first we have to write using right hand thumb rule. Clear? Right hand thumb rule. Okay, I hope this is clear. So just curl your fingers in the direction of rotation. Like now, let's suppose if I am observing this disc from the left hand side, so sense of rotation will be what? Clockwise. Again you have to use what? Right hand. Curl your fingers in the direction of rotation, like clockwise sense, and your thumb will show the direction of rotation. Now again, if you observe from here or there, the direction will be what? Same only, right? So this arrow plays a very important role in the gyroscope analysis. Now, for example, if I take the case of aeroplane, let's suppose we'll take the case of aeroplane later. Let's suppose if I say my shaft, this is what my shaft is there. I'm just drawing the diagram so that you will get to know what is the question here. I'm not writing the question. I will just give you an example or situation here. This is my shaft here, and it is rotating anti-clockwise from the right hand side. Anti-clockwise from the right hand side it is rotating. Now this shaft has been what? Turned right. Now this shaft has been turned right. Consider this point. This is the shaft. This is the shaft, and from the right hand side it is rotating anti-clockwise. Okay, that is the point they have given. Now this shaft has taken the right turn. This shaft has taken the right turn. Okay, I don't know how it has taken the right turn. Forget about the reason of the right turn. Now consider, focus on this thing. It has taken the right turn. Now if it has taken the right turn, what effect you will see? What are the effects that we will see here in this case that we need to analyze? Okay, try to understand. Shaft, if you observe from right hand side, it is having anti-clockwise sense of rotation. Now it is having a turn like this. Right turn it has taken. So when I say right turn, I am observing from the top. So right turn it has taken. So obviously shaft from the right hand side, anti-clockwise sense of rotation. So this is what this is the direction of rotation. This is what the direction of rotation only. Now I will not consider the shaft. I will not consider the shaft now. I will focus on the direction. I will focus on this arrow. Now as the shaft has taken the right turn, so how this will move, how this rotation vector will move, like this only, simple. But all this happening in a horizontal plane. This right turn, left turn will take place in the horizontal plane. So now consider here. Initially it is like this. Okay. Initially it is like this. Yes or no? Initially it is like this. Now it has taken the right turn, so it will be like this. At any angle it has turned. Let's suppose any theta or any alpha angle it has turned. Okay. So this kind of this kind of turn it has taken in the horizontal plane. So obviously I've mentioned here, this is the vertical plane, this is the horizontal plane. Okay, like this, and generally we call this as a profile plane. Okay. So this kind of movement of the rotation vector is there. Now as the direction of the rotation vector changes, obviously change in the velocity means change in actually change in velocity basically means acceleration will be there. Are you getting the point? Change in the direction of velocity basically means the acceleration will be there. Acceleration, angular acceleration is there, so obviously some torque will also be there, right? That is the point we should consider here. Now see, so this kind of point here you should understand as the active gyroscopic couple. And this will be what? The reactive gyroscopic couple. This one, wherever you have taken the turn, no, in that direction only, the active gyroscopic couple, opposite to that reactive gyroscopic couple. See, everything is happening in a horizontal plane. Everything is happening in a horizontal plane. That is the point you should understand. So when this reactive gyroscopic couple is there, and you need to understand what will be the effect of this reactive gyroscopic couple, again you have to use right hand thumb rule. Again you have to use the right hand thumb rule. Okay everyone. So what you will do, just consider the arrow here. You will put your thumb in the direction of arrow. Now you have to put your thumb in the horizontal plane itself. You have to put your right hand in the horizontal plane and arrow in the direction of, your thumb will be in the direction of arrow. Now this fingers will show the effect. This fingers, how it is curled like this? It is curled like this. Okay. So what will happen to this shaft? This shaft will have, see, initially the shaft was like this. Try to understand. Initially the shaft was like this. Now because of this reactive gyroscopic couple, it will be like this. It will be like this. The front part goes down, the rear part goes up. Why? Why is it so? See, right hand, the thumb in the direction of arrow, considering that my hand is in the horizontal plane, because everything is happening in horizontal plane, like this. Now fingers curl like this. Fingers curl like this. So what will happen? This front part goes down. Obviously when it goes down, the rear part goes up. Simple. Is this point clear everyone? Yes or no? Okay, is this point clear? So now we'll move on to the case one, aeroplane case. Very simple case is there. Again, basic part we'll discuss here. Okay, basic part we will discuss. Okay, now see. Then ship case we'll also discuss, but first aeroplane case. So see, they will ask this thing. Okay, so let's suppose if I draw the Okay, considering this as an aeroplane, right? Right. So let's suppose this is the nose part, this is the tail part, and they will give some. They will say, okay, there is a propeller shaft in the aeroplane which is having the anti-clockwise sense of rotation from the right hand side. Like that, they will give. The propeller shaft in the aeroplane is having anti-clockwise sense when you view from the right hand side, when you observe the shaft from the right hand side. So when it is having anti-clockwise sense of rotation, I will use right hand thumb rule. Arrow will give me the direction of rotation in terms of vector. So okay, I will draw like that. So first I will draw the my coordinate system here like this, x, y, and this is what, z. Now see, so now they will further in the question they will say what? They will say, let's suppose the aeroplane taken the left turn. Now in this case I will take left turn. Left turn it has taken. Left turn it has taken. So what will be the effect on the aeroplane? So initially you should understand, right? So this is the horizontal plane. Okay, this is the another plane. Now, as the shaft is what having anti-clockwise sense of rotation from what? From the right hand side. So vector will be drawn like this. Vector will be drawn like this. Now it has taken the left turn. So left turn will be like this. So for that, what will happen? For that it will be the active gyroscopic couple, and there will be a reactive gyroscopic couple. There will be one reactive gyroscopic couple, and everything is happening in the horizontal plane itself. Are you getting the point? Yes or no? Please tell me. Everything is happening in a horizontal plane. Now you should tell me what will be the effect of the reactive gyroscopic couple that I have shown with the red color here. The yellow one is the active gyroscopic couple, red one is the reactive gyroscopic couple. Yes or no? Tell me fast. Please tell me fast, guys. What will be the reactive gyroscopic couple? Effect of reactive gyroscopic couple on the aeroplane. Now, see again, please remember this point. You have to what? Use right hand thumb rule in order to understand what will be the effect on the aeroplane because of this reactive gyroscopic couple. Now see, arrow is what? Like this. If I have to use the right hand thumb rule in the horizontal plane, it will be like this. The arrow is what? Pointing away. So it will be like this. Now fingers will curl like this. Now in this case, what will happen? The nose part will goes up and the tail part goes down. Is this point clear? Yes or no? See, in this case, what will happen? Nose part will goes down and the tail part goes up. Now earlier in the previous case, what has happened? Nose part goes what? Down and the tail part goes up, right? Clear everyone? Clear? Now is this point clear? Yes or no, guys? Please tell me. See, pointing away, this point, the thumb is pointing away. So nose will goes up. Okay, nose will goes up. Okay, I've drawn just opposite to that here. No worries, we'll change the diagram here. See, reactive gyroscopic couple, nose will goes up. So it will be like this. Nose goes up, tail goes down. Clear? Okay, everyone. I hope this is clear, right? So now moving on to the next part, like ships. See, in ships, some basic terminologies we should remember. Otherwise, we will not be able to solve the problem of gyroscope from the ships part. Okay, but before that, you should understand what is the formula of the gyroscopic couple, right? See, gyroscopic couple formula I omega into omega, omega s and omega p. This formula you should remember. Omega S is what? The omega of spin. Omega P is the precision velocity, precision angular velocity. What is that? See, actually the spin is, for the propeller shaft you can easily calculate the angular velocity of the spin. But what is the precision? Precision velocity, see, I will show you in the diagram itself. If omega S is this one, this will be what? Omega P, because you are giving the turn like this, right or left turn you are giving, no? So obviously about this axis you are giving the rotation, about this axis you are giving the rotation, and you are observing the effects on this z axis, and you are observing the effects on the z axis, right? Okay, now moving on to the shifts part. So in this shifts, what will happen? See, this is the stern part, this is the bow part, that you should remember, everyone, because in the question language also they will use such terms. In the question language also they will use such terms. Remember this point, stern and the bow. Now you should understand, this is the transverse axis, this is the longitudinal axis, this side is known as port, this side is known as starboard. So if I take left turn, I will say the ship is moving towards port side. Now if it is taking right turn, I will say it is moving towards starboard. Left and right is decided when I am observing the ship from the top. Is this point clear? Obviously, is this point clear, na? So if I take the left turn, it will be towards port. If it is taking towards right side, it is the starboard. Now, three cases will be there in the case of ships. Case number one. Case number one is what? Pitching case, steering case, third case rolling. Now, pitching and steering, you need to understand the difference. Pitching will be there when it is having a what? Angular motion about the transverse axis. Is this point clear? When it is having a motion about the transverse axis, it is known as what? Pitching, like this. Okay. If this is the ship, consider my hand as a ship, it will move like this. Okay, it will move like this. So it is a pitching case. Right, everyone? Steering basically means it is taking left turn, right turn. Rolling is the angular motion about the longitudinal axis. Angular motion about the longitudinal axis is what? The rolling motion. Now, first we will consider the steering case. Okay, first we will consider the steering case. Now see. Now, if in the steering case, what will happen? Let's suppose the ship takes the right turn, but for that they will not tell the it is taking right turn. They will say it is moving towards starboard. Clear, everyone? It is moving towards starboard, like this they will tell. So let's suppose it is taking towards starboard movement, it is taking, so it means right turn it is taking. And again they will mention there is some propeller shaft is there, and this propeller shaft is having anti-clockwise sense of rotation or whatever kind of sense of rotation they will give. Accordingly, we will draw the rotation vector. Accordingly, we will draw the rotation vector. Yes or no, guys? Please tell me first. Okay. Now see, assuming we will assume that it is having anti-clockwise sense of rotation. So if it is having anti-clock sense of rotation, we can easily draw the rotation vector like this. Now, if it is moving towards the starboard, so it will be like this. Okay. So this will be the active gyroscopic couple. This will be opposite to that reactive gyroscopic couple. Again, same thing will happen. What will happen, guys? Arrow, in the direction of arrow, you have to place your thumb. Put your thumb in the direction of arrow like this. It is happening in horizontal plane. Remember this point. The fingers will show you. The fingers will show you what will happen. According to this, what will happen? The bow part will go down and the stern part will go up. Bow part will go down and the stern part will go up. Is this point clear, everyone? Is this point clear? Yes or no? See. Again, right turn it has taken. Right turn it has taken. Please try to observe. Right turn it has taken. So active gyroscopic couple, reactive gyroscopic couple. Arrow is pointing like this. I have used my right hand in the horizontal plane. Now fingers like this. So whatever the front part is there, it will go down and the rear part will go up. So now if you observe, the front part goes down, it means bow. Bow part will go down and the stern part will go up. So that is the point. So that is steering case is just similar to the case of aeroplane. Now we will discuss the case of pitching. Pitching basically means what the motion with respect to angular motion with respect to this transverse axis. Either it will be pitching down or up, like that it will be there. Okay, so you can consider any case, right? It's your choice. So pitching case I am considering. So pitching up, let's suppose. Pitching up case I am saying. Okay, so now the motion will take place in vertical plane. Again same, the propeller shaft sense of rotation is same, right? So like this. Now if it is pitching up basically means the rotation vector will turn like this. Active gyroscopic couple, reactive gyroscopic couple. Now please try to understand, everyone, the arrow is what? Downward. Now you have to use your right hand in the vertical plane. In the vertical plane you have to use right hand. Thumb goes down, the fingers will curl like this. Fingers will curl like this. Now when the fingers will curl like this, what will happen? The ship will steer. The ship will steer towards starboard. Are you getting the point? Clear everyone? Okay everyone, is this point clear? Now see. So pitching up, opposite to that you can also discuss, opposite to that a pitching down case also you can discuss. In that case what will happen? Just opposite to this one. It will pitch, it will steer towards port side. So pitching up, rotation vector goes up. Active gyroscopic couple, reactive gyroscopic couple. Reactive gyroscopic couple arrows down. So we'll keep our thumb in the downward direction. We'll see the rotation of the finger, how the fingers has been what rotating a curl. So based on that we'll say my ship will move like this. Now if the ship moves like this, what will happen? It will move towards starboard only. Now if I talk about the rolling case, guys, please understand. Rolling case basically means the rotation about the longitudinal axis. Now whatever the rolling motion is there, guys, so direction will be what? Parallel to the what? Parallel to the existing rotation of the propeller shaft. Existing rotation vector is there in the same direction only. If you give the rotation, so both the vectors will be parallel. Both the vectors will be parallel, and there will not be any gyroscopic couple in case of rolling. So we'll write here as a note point we should add. In the case of here itself we'll mention no gyroscopic couple. In rolling. Clear everyone? I hope this is clear. Next chapter, balancing, very easy, simple mechanics concepts you have to apply. Okay, simple mechanics concepts you have to apply, and you can easily solve any problem related to balancing, guys. Okay, till now, is there any doubt? Is there any doubt you are having? Please tell me fast. Is there any doubts? Okay, no. So okay, we'll proceed in this chapter. Balancing of rotating masses, first of all we'll discuss in that first case, single revolving mass, case 1. Now this is the eccentricity of the mass, that is what placed from the axis of the shaft. This is the eccentricity, or you can also consider the, or even you can also consider the radius of rotation also, right? Very good evening Amit, very good evening. So let's suppose this is the disturbing mass. So actually this will be the radius of rotation. Let's suppose this is the mass of the disturbing mass, right? Now you should understand, in order to balance this mass, I can place a balancing mass here itself. So let's suppose this is the balancing mass we are having. This is the radius of rotation of balancing mass. Now if if we provide this balancing mass and now it is what balanced, so simple equilibrium equations I can use, like the net force equals to 0. In this case there will not be any moment. Why? Because the line of action of the force is what, same only, so there will not be any moment. So net force will take 0. So here it will be like this, mr omega square. Here it will be like this, mb rb omega square. Clear everyone? So we will write like this, mr omega square equals to mb rb omega square. Okay everyone, now see, omega square will be what, cancelled out because the speed of rotation will be same. M into r will be equals to mb rb. So from this relation you can calculate any unknown parameter. Okay, I hope this point is clear. Okay, right, now we'll move forward here. Now see, now we'll see what will happen. Now actually again in this case also, if there is no possibility that we can place a mass just in a line of this disturbing mass, so what will happen, we have to place the mass somewhere else. So let's suppose if I place the mass here like this, so this is the mass m, which is what, disturbing mass, radius rotation r. Now with this mass, single mass, I cannot balance this one. With this single mass we cannot balance. Why? Because see, there will be one force here, there will be one force here. So obviously if this force and this force will be equal, a couple formation will be there. A couple formation will be there, and we need to what, balance the system completely, both in the terms of force and as well as in terms of moment. Are you getting the point? Both in terms of force and in terms of moment we need to balance the system. Otherwise we cannot say that our system is totally balanced. Right everyone? So what we will do here, we'll again connect one more mass here. So let's suppose I will call this balancing mass 1, balancing mass 2. See, in this case we have to place two balancing masses in order to balance this one. Yes. Now see, this is RB1, this is RB2. Now considering this point as A, B and C. Now again equation of motion is what, same only, summation of forces or the net force I can use like this. I will use the equation like this. Net force equals to 0. This is the first equation. Now how we will use here? Okay, so mr omega square equals to mb1 rb1 omega square mb2 rb2 omega square, like this. So omega square will cancel out. You will have mr equals to mb1 rb1 plus mb2 rb2. So this will be the first equation that you can utilize. Another equation you will have from this one, net moment. Again see, you can use summation sign or the net sign, it's your choice. Net moment should be what, 0. Then only we'll say our system is what, perfectly balanced. Right. So this is one equation, this is another equation. So these two equations will help you a lot. So now where I should take the moment? You can consider any point, A, B or C, whatever point you can consider, any point you can consider. It will be based. See, now how you will decide? You should ask, sir, how I will decide which point I have to select? See, it depends which parameter you need to calculate. Okay, and which parameter you know. Based on that only I can select the point, right? So let's suppose if I select the point A, so moment about point A will be because of this force and this force. Okay, if I select the point A, moment of this force will be anti-clockwise, this force will be what, clockwise. Like that I can have. So let's suppose if I write moment about point A is 0. So m into r into omega square. This is the force. We need to multiply the distance. So let's suppose the distance is given a distance L, L1, let's suppose. So L1 we need to multiply equals to, because it is anti-clockwise, this is what, clockwise, MB2 into RB2 omega square into L2 distance. Let's suppose this distance is L2. Clear, everyone? I hope this is clear. Okay, now moving forward. Now see, again one more case is possible, right? What is that case? What is the possibility of the next case? See, everyone. Now it can be possible that you cannot place the balancing mass on both the sides. You can place the balancing mass on one side only. So in that case, what you will do? You have to place one balancing mass here and one balancing mass, okay, here, like this. Okay, so actually, see, forget about the placement. First, you should understand what we have to do. We have to balance. We have to balance the system, right? Both statically and dynamically we need to balance. Now, let's suppose they are saying you cannot place the balancing mass on one side. Okay, you cannot place the balancing mass on one side. So what will happen? So let's suppose first balancing mass you have placed like this. Now obviously one force will be like this, one force will be like this, and let's suppose if it is equal to this force, a couple formation is there. So that is what unbalanced system is there. So what we'll do here? Now let's suppose you will say, sir, I will place the mass here. So again, clockwise moment it is having, clockwise moment it is having. Okay, so considering this point, you will have a clockwise moment. So what you will do here, you have to place the mass here in such a way that, let's suppose this is a point A. At point A, net moment has to be what? 0. Now if I place the same mass here in the same direction only, in the downward direction only, if I place the mass, both will have a same direction of movement, so they will not get cancelled out. I have to place the next mass here like this, because it will have a moment like this, anti-clockwise, it will have a clockwise. Then it can be balanced. Then it can be balanced. Again, what equation of motion you have to use? Net force 0. I hope this equation number 1, this is equation number 2, both the equations are clear. Simply you have to apply the equation and solve the numerical of the balancing mass system, right? Now see, several revolving masses case, again one of the most important case from which the GATE has been asked, the GATE has asked many questions from this topic, several revolving masses. Now actually this diagram you will see when you observe from the side, when you view from the side, no, you will feel that such kind of diagram you will observe. Such kind of diagram you will observe. Is the point clear? Yes or no? First of all, tell me. You will observe such diagram if you observe this rotating masses from the side. But when I observe from the front, I will not see the shaft here. I will see the okay. Are you getting the point? Hi Pragya, how are you? So try to understand two different frame. See, I have shown two diagram here so that you will be able to understand how it looks. Okay, I have shown two different diagrams, right? So when I am observing from the side, so obviously this is the shaft here. Only as a point you will observe. So let's suppose this is the shaft. Please try to understand. This is the shaft. If you observe from the side, you will see the point only. You will see the point. But when I see from the front, I will see that whole length. Are you getting? So here you will see the whole length of the shaft also. But when you see from the side, only point you will see. Clear? So I hope this point is clear. Now two different ways of representation will be there. It depends upon the examiner which frame of reference, which particular diagram they will give you. But from the diagram itself you can understand, okay, this are the disturbing masses. I have to place some balancing mass here so that my system will be what? Under balanced condition, right? Okay, I will tell you the approach here. See, obviously it will be confusing, right? Because you need to place the balancing mass to balance the whole system. Now, when I say balance the system, you need to consider two important things, right? The force and the moment. You cannot call your system which is having the force balance that it is completely balanced. No, it will not be completely balanced. For the complete balancing, two things you need to ensure, that force balance is there, moment balance is there. If force balance and as well as the moment balance is there, then you can easily say my system is completely balanced, because force and moment both can create the disturbance. So we have to make sure that we have to make sure both the moment and the force both are balanced, right? I hope this is clear. Now we'll see how the several revolving mass case we can solve. Now see, let's suppose this is what reference axis, let's suppose x. Now one by one we'll mention the angles here. See, okay everyone, now see, and this is what the angle. So this is m1 theta 1, m2 theta 2, m3 theta 3, m4 theta 4. Clear everyone? Yes or no? So like this we have mentioned. Now you will be wondering, sir, why you have mentioned angles like this? Actually, I will take the angle from one of the reference axis. All the angles I have taken from the reference axis. Is this point clear? I have taken the angle from the reference axis, so that I can easily write down the horizontal component and a vertical component. So that there will not be any confusion. There will not be any confusion. Okay everyone? Okay. Now see, in order to balance the system, two equations that we have discussed also. This two equation we need to follow, right everyone? Now see, okay, here itself I will mention, okay, so that diagram will also be clear and you can easily mention everything. So now see, this is the case in which different masses are there, I need to balance. So as all the masses, disturbing masses are connected at a point, I can easily attach one mass and I can balance the whole system. But if it is placed at different locations, in that case I cannot balance the whole system with single mass. But in this case I can balance the whole system with single mass. Why? Because all the disturbing masses are get connected at a single point. Is this point clear? Right. Now let's suppose some balancing mass if I placed, right, I will use a different color here so that you will get an idea. Okay, let's suppose some balancing mass. And I will call this MB. I hope this is clear. MB I will call, right? MB is the balancing mass, radius of rotation RB. Okay, simple. Now see, if I use this equation, summation of forces equals to 0, you should understand it will be 0 only when these two things will be satisfied. Summation of force along horizontal 0, summation of force along vertical 0. Summation of force 0 basically means, or you can even write resultant is 0. Resultant will be 0 when summation of forces along horizontal and vertical direction is 0. Individually it has to be what? 0. Individually it has to be 0. Okay. Now we will ensure this thing, summation of force along horizontal 0. So we'll write first equation. Okay, so what is the first equation? See, you will have mr omega square. Okay, we'll remove this one so that we can easily write m1 r1 omega square. Okay, that is the one force. Cos theta 1 we have to take for the horizontal component. Similarly, we have to write like this, m2 r2 omega square cos theta 2. Okay, like this we have to do for third mass also. Plus m4 r4 omega square cos theta 4. Okay, like this it will be there, plus the balancing mass. Because of the addition of the balancing mass, our system gets balanced, right? MB RB omega square cos theta b equals to 0. In a simple format, I can directly write like this. MB RB. See, omega square will get cancelled out. Minus. Because let's suppose if I've taken MB RB omega square cos theta b in the left side only, and everything I've taken in the right side. So minus sign will come into picture. And I can write summation to R cos theta. So this is the equation you should understand first of all. Because summation fx 0 I have taken, no? Yes, obviously, in many cases you will see such kind of case. In many practical examples you will find such cases. So let's suppose at one point, see, now you will have a confusion. Why? Because you will say, sir, some mass has been attached like this. No, it is not like that. Actually, what will happen? No, let's suppose a shaft is there in which a disc we have placed. Some rotor is there. Now for that rotor, geometric center and mass centers are different. That's why the disturbing force will come into picture. Okay, I will tell you this thing. Okay, see, this is my shaft. Okay, and I have placed a rotor here. Okay, so geometric center of a rotor is this one. Now, if the geometric center and the mass center are same, then there will not be any disturbing force. But from the manufacturing default, okay, because of the manufacturing default here, or we can say defect basically here, a manufacturing defect will be there. During casting or during the production of the rotor, the mass center and its geometric center are not same because of the manufacturing defect. As a manufacturing defect, it gets shifted here. Now, this is what the mass center we are having, MC mass center, and this is the geometric center GC. Now, if the mass center is here, so obviously the resultant force will be acting here itself. So that's why, because of this eccentricity, you will have the disturbing force. Otherwise, it will not have the disturbing force. If it is, if this mass center is at the axis of rotation, if the mass center is at the axis of rotation, there will not be any disturbing force, and there will not be any problem of vibration also, right? I hope this is clear. Right, now come back to the previous part. From summation fx 0, summation fy, summation fx we have already taken. Now similarly we will write here. Obviously, in the case of vertical forces, sine parameter will come into picture. Okay, now see. Okay, clear? Is this point clear, everyone? Or tell me fast, is this point clear? Right, so like this, two different equations will be there. Now we will utilize both this equation to get our unknown parameter. Whatever they will ask, we'll solve for that one. Okay, now see everyone. So let's suppose this is equation number 1, equation number 2. So if I divide, let's suppose equation 2 with equation 1, so what I will get? I will get tan theta b. Now if I square and add both the equations, what I will get? See. MB RB whole square equals to summation M into R sin theta whole square summation MR cos theta whole square. So MB RB, if you want to calculate, take the under root of this one. summation mr sin theta. Okay, done. Done, everyone. I hope this point is clear. So this is the relation number 2 we are having. Actually, this relation and this relation will help you to solve the unknown parameter they will ask. Now in this case, don't cancel out this sign. Don't cancel out this sign, because if you cancel out this sign, you will not be able to identify in which quadrant actually you have to place your balancing mass. Right, everyone? Okay, welcome Pragya. So I hope the balancing concept is clear to everybody. Balancing of the rotating masses. Right? So actually these are not the masses, right? Actually what happened, no, in the rotor there will be what, a manufacturing defect will be there. Because of that manufacturing defect, geometric center, mass center are not same. If the mass center is at the axis of rotation, there will not be any disturbing force. Okay. Why do we consider the radial acceleration only? Oh, see, try to understand this point. Actually, what will happen? No. See, if this is the shaft we are having, okay, and let's suppose some mass is there. So it is rotating. So you will have this centrifugal force mr omega square, right? So it is what are like this. It is having a rotation like this. So obviously the centrifugal force will be acting like this. Okay. So this force will come into picture, not in the radial direction. See, this is what the longitudinal, actually this is what the radial direction. In the radial direction we have considered it. Now in the longitudinal direction, if you consider like this, there is no movement at all. There is no movement at all, right? The forces will not be there. Okay. See, consider this point. This is the shaft and the mass is what rotating about this shaft. Okay. So force will be always away from the shaft axis. Force will be always away from the shaft axis. It will not be like this. Okay. It will not be along the shaft. Okay. This point you should remember. Right. Now, this one, balancing of the reciprocating masses. Now, only few cases they have asked the question from the balancing of reciprocating mass. So you should consider this as the important one. Consider this one as the important one, right? As compared to rotating masses, because lot of time they have asked question from rotating mass, but reciprocating masses only few questions they have asked. Okay. Right. See. So actually what will happen in this case, everyone try to understand. So there will be a acceleration, okay, or the unbalanced force that will be acting on the frame, which is nothing but the mass multiplied by the acceleration. Mass of the reciprocating link we are taking, m into r omega square cos theta plus cos 2 theta divided by n. Now this is the unbalanced force here. Now please remember this point. If I open up this bracket here, so I will get this thing. Okay. Now very important point, guys, very important. This part is known as the primary unbalanced force. This point will known as the secondary unbalanced force. Primary unbalanced force and the secondary unbalanced force. Why we are calling it primary and then this one is secondary? Because the primary, whatever we have called as primary, it has the more magnitude as compared to the secondary one. Is this point clear? Right? Yes or no? It has the more magnitude as compared to secondary one. Why? Because the numerator and the denominator, if you look at the denominator part, it is the n, it is the ratio of L by R, length of connecting rod divided by the crank radius, and the length of connecting rod is generally what, very it has the length of the connecting rod will have a high magnitude as compared to length of the crank, right? So that's why based on the magnitude only we are calling it as the primary and this one as secondary, based on the magnitude. Now whenever we'll try to balance this reciprocating mass case, the unbalanced force in the reciprocating mass case, we will not be able to balance it completely. Rotating mass case we can balance completely, but in the case of reciprocating mass we cannot balance it completely. Remember this point. That's why we are using the partial balancing. That's why we are using the concept of partial balancing of primary unbalanced force. See, actually first we'll try to balance primary, then secondary. So secondary you don't have to discuss that thing. Primary will focus on the primary one, right? So partial balancing of primary unbalanced force we'll discuss here. Now we'll consider only the primary one, that is mr omega square cos theta, right? Theta is what? The crank rotation theta, like this. Actually what will happen now, for this we'll place the mass here, some balancing mass will place. Now what will happen now, this angle will also be theta. So here what will happen, if you see, here there will be one component, here there will be one component. Here the MB RB omega square cos theta, and here MB RB omega square sin theta. Clear everyone? Is this point clear? MB RB omega square sin theta, like this it will be there. So MR omega square cos theta, and this one, this one. Now actually because of the partial balancing only, will not cancel out this thing, otherwise what will happen, the maximum force will be there in the vertical direction. Okay, so we have to understand this point. So as the partial balancing is there, you should understand what is the case of partial balancing. It is the case in which we will not completely balance this force. So what we'll do, we'll do some amount, some fraction of this force we'll try to balance. We'll not completely balance this one, because in that case we'll have a problem of this force. And you should know the maximum value of this force is nothing but the hammer blow. Are you getting this point? Yes or no? That point will be known as the hammer blow, the maximum value of this force, the vertical force, right everyone? Okay, yes or no, please tell me. Right, now see, your MB RB will be equals to C times MR, and your C will have a value from 0 to 1. Okay, now obviously when C value equals to 1, what will happen? Okay, C value equals to 1, what will happen? Complete balancing. That is not the case. That's why we have written less than sign and greater than sign here. Will not put the value of C equals to 0, will not put the value of C equals to 1. Both the cases is not practically possible, right? So this relation you should understand. Okay, they will give the value of C. You have to place the value of C here. Okay, as a percentage they will give, like 70% of the mass you have to balance, 80% of the mass you have to balance, 65, 75, like that they will give. As a percentage they will give. So you have to use this relation MBRB equals to CMR. Now what questions they can frame from this one? See, they will frame net force along line of stroke. So it will be equals to MR omega square cos theta minus MBRB omega square cos theta. Now try to understand. If I replace MBRB, so what you will have? MR omega square. See, I will write completely here. Now common part we will take here. Okay, so we can write it here itself. One minus C. Okay, 1 minus C MR omega square cos theta. That is the value of the net force along the line of stroke, right? Along the line of stroke, this is the net force. Now what is the net force perpendicular to the line of stroke also? perpendicular to the line of stroke, there will be a force here. Okay. See, previously we have mentioned no here. So what is the net force? This one only, right? Because along the line of stroke we have to take the difference. Please. Okay. Now see, here itself we'll write here. No, don't worry, we'll write here itself. Perpendicular to LOS, that is line of stroke. Here MBRB omega square sine theta, and you can replace this thing MBRB as C into M into R omega square sine theta. Now in some cases they will be asking to find out the resultant force. Okay, resultant force. What will be the resultant force? Simple. Take the square and add. Net force along line of stroke. Take the square plus net force perpendicular to LOS. Take the square. Right, everyone? So that will be the resultant force. I hope this is clear. Now moving to the next chapter, and one of the most important chapter, it is one of the most important chapter, I would say. Right? Now in this one, the very first part that you need to understand is the undamped free vibration for the single degree of freedom system. Now in this case we will discuss this vibration chapter in such a way that all the questions that can be possible will be what completely covered in this session only. Okay, we'll discuss entire vibration in such a way that all types of numericals that are possible in vibration chapter, it will be covered. Okay, we'll discuss all the important relations, concepts, okay, from which we can solve the numericals. Right, everyone? Now see, actually what happened in the single degree of undamped free vibration case. So I will first draw the diagram here. There is a mass here, okay, spring having a stiffness K. Now this is what a very simple case of the free vibration, but you should understand the first of all equation of motion. Okay, you can get this equation of motion using Newton's second law. Simple. Now how you will represent this equation? K by M. K by M is actually omega n square. This format of equation you should know at least. So that is the point number 1 regarding this example. Next, what is omega n? Natural frequency, that is equals to under root K by M. So what is the important thing that we need to take care in this formula? We have to make sure that the value of K is in Newton meter, but they will give definitely in kilonewton per meter, Newton per mm, Newton per centimeter, like that they will give. Okay, so I will mention here K unit Newton per meter, mass obviously kg. Now this is what having a unit radian per second. So you can also calculate the frequency in terms of hertz using this formula. In hertz you can calculate. Clear? Okay. Now what is the time period? So time period will be nothing but the 1 upon frequency. Simple. Yes or no? Is this part clear? Now for this equation of motion, guys, this equation of motion you should understand. What is the solution they have provided? X equals to capital X sine omega n t plus phi. This is the solution you should remember. Capital X is the amplitude. Amplitude is the maximum displacement of your system from its mean position. Okay, omega n is the natural frequency, t is the time period, phi is constant actually here. So this is the formula you should remember, everyone. Now, is there any problem in this case? Anyone, please tell me first. Okay. Now, one note point, as a note point you should remember here. See, if I use this formula, no, you should remember I have not considered the mass of the spring. If in the question they will give, okay, consider the mass of the spring as well. So in that case, the formula will change. And how the formula will change? Please consider this thing. Where ms is mass of spring. Okay, mass of spring. Clear, everyone? Yes or no? Right? So this is the point you should understand. So mass of spring. Next thing, how to solve numericals in which a natural frequency they will be asking, right? So two methods are there. Methods to solve a natural frequency problem. Natural frequency problems. Okay, first method, Newton's second law. Okay, third one, second one actually, second method, energy method. Okay, in Newton's second law, you can even call it the torque method also, because in some cases a rotation will be involved. So in that case, torque will be there, right? So actually we will discuss this energy method. So actually in this energy method, we'll assume that total mechanical energy is what conserved. Is what constant. Actually we are considering no dissipation of energy, that's why we are considering this thing. So if it is constant, if I use differentiation, if I take the differentiation of the total energy here and differentiate with respect to time and equate it with 0, so with the help of this relation, we will get the equation of motion for the case in which no dissipation of energy is there. That is what no damping is provided, undamped system is there. So we'll use this equation, energy method. And Newton's second law or the torque method, summation of all the forces 0 and summation of all the torque acting in the system equals to 0, like that, right? Now, three cases are there that you should remember. Possibility is there that they can ask a question from this one. Okay, now see. Now, in the longitudinal vibration, see what will happen, no? So, in this case, you should understand this mg, the weight, equals to k delta. And you can write k by m as what? G by delta. But you should understand first thing, that delta is the static deflection. Delta is our static deflection, right? So, in order to calculate the static deflection, see in this case, you have to use the formula from the strength of material, right? I think in this case, delta formula, if you remember in strength of material, you have discussed PL divided by AE, right? This is the formula for the calculation of the static deflection. So directly by using the formula omega n, instead of writing k by m, we will write g by delta. Okay, like that you can solve. In this case of transverse vibration also, you can use omega n equals to g by delta. Now, let's suppose this is the cantilever and pointed mass is there. So in this case, we will have delta formula as WL cube by 3EI. This is the formula you have to use. Yes or no? Right. So this formula will be there from the strength of material concepts, right? In the SOM subject, we have discussed this thing. Like slope and deflection chapter will be there. In that, different cases will be there. So you have to remember the slope as well as the deflection formulas. Very important. Lastly, torsional vibration. Guys, see. Actually, this is a disc here, like this. Okay, like this, a disc will be there. Now, in the disc, again, if you want to write the natural frequency, you will write like this. KT. Torsional stiffness divided by the I, that is the mass moment of inertia. Actually, KT is nothing but the torque divided by theta. Okay, torque divided by theta is there. So if you know the torsional stiffness, you by calculating T by theta, putting this value here, you will get a natural frequency here. I hope this point is clear regarding longitudinal transverse vibration and the torsional vibration. Is there any doubt? Any doubt till now? Please tell me fast. Is there any doubt? Okay, now we'll move forward here. We'll move forward and we'll see the next case, that is from the damped vibration. Damped free vibration case we'll discuss here. Now see, very important. And see, mostly you will see the numerical from this damped cases. This is a spring we are having. And this is the mass, let's suppose. Spring having stiffness K, damping coefficient C. Right? Now, very important point, please see, in this case, spring damper system. First of all, you should understand equation of motion for this case. Equation of motion. The first point is what? Equation of motion. It is like this: mx double dot cx dot plus kx equals to 0. And if you want to write it in a new format also, you can write it like this. Okay. Now, you should understand here, there is a damping factor that you should remember, C by Cc. Damping coefficient divided by critical damping coefficient. Okay, this formula is what very important. Damping coefficient divided by critical damping coefficient. Now, see, this C by Cc can be written as 2m omega n, Cc value, and even you can write like this, 2 root km. So, this formula you should remember. Now, if this formula is clear, now you should understand how we can write this equation in a definite format. Yes or no, guys? Please tell me fast. Clear? So now see how I can write this equation. You should remember this one also. This is the equation, right? So this is the equation that you should remember. Okay, very, very important. So let's suppose if the case of rotation is there, in that case you will write the equation in this term. Okay, like this will be there in if the rotation case is there. If the rotation case is there. Now I hope this much part is clear, because whenever such example they will give spring stiffness K, damping coefficient C, mass M, directly you can write this equation. But make sure that the coefficient of x double dot is what? 1. Make sure that the coefficient of x double dot is 1. In that case, coefficient of x dot will be equals to this one, coefficient of x will be equals to this one, right? Like this. Now, types of system: damped and undamped system. Undamped basically means what? No damping. Damping factor 0. Simply we will write no damping. Now, damped system, 3 cases possible. See, underdamped, critically damped, and overdamped. Okay. Now see what will happen. In the underdamped, the psi value is less than 1. Critically damped, psi value equals to 1. Overdamped, psi value greater than 1. Now you should understand this point. In the case of critically damped and overdamped, oscillation you will not see. There will not be any oscillation in the case of critically damped and the overdamped case. Yes or no? Right? But in the underdamped case, you will see the oscillations. That is what the vibration part. So we'll focus on this underdamped. We'll focus on this underdamped. Right? See. Underdamped system basically means psi value less than 1. Remember this point. Psi value is less than 1. Yes or no? Clear everyone? Psi value will be what? Less than 1. Right. Now actually when underdamped system is there, for that the solution of equation will be like this. I'm just writing direct solution here so that you will get an idea here. E to the power minus psi omega n t sine omega d t plus phi. Now see, very important point guys. Very important point. This solution is what very important, and you need to analyze this solution also, right? Now if you consider this thing as an amplitude, okay, this is an amplitude part, and you will see amplitude decreases exponentially with time. Okay, amplitude decreases exponentially with time. Is this point clear? And this sign represents what? The repetition of what? Repetition of motion. The sign, see, this sign function represents what? The repetition of motion. So obviously oscillation will be there in this case, but with the damped frequency. And what is the damped frequency formula? Okay, this is the damped frequency formula that you should remember always, right? And the damped frequency will always be less than natural frequency only, right? Remember this point guys. Amplitude decreases exponentially with time. Damped frequency formula is this one. Now one more thing that we should discuss here is next, logarithmic decrement in this case only, right? Actually what will happen? The ratio of two successive amplitude is what? Constant here. You should understand this point. Ratio of two successive amplitudes. Ratio of two successive amplitude is constant here. Okay. Now see, x0 by x1, x1 by x2, x2 by x3, and so on equals to constant, right? You should understand this point. Now if I take the natural log of this one, we will get the logarithmic decrement actually. So what is logarithmic decrement? See, logarithmic decrement I can represent with del. See, I will use different notation here so that it will be properly visible to you. That is what we are having, the notation of logarithmic decrement. So it is actually equals to natural log of ratio of two consecutive amplitudes, right? And if you solve, you will get the formula like this, that you should remember for the gate. Directly you should remember the formula. Okay, this is the formula. Now third, there is one more formula here that you should remember. It is equals to 1 by n ln x0 by xn, where n represents what? The number of cycles. N is what? The number of cycles. Clear everyone? Yes or no? N is what? The number of cycles. Okay, very important three relations that you have to remember. Relation 1, relation 2, relation 3. All three formulas are what? Equally important, and it depends what important parameter they have given in the question. Accordingly, we will select the formula. Based on the parameter given in the question itself, we will select the formula and we will implement it and we will get the solution from those relations, right? And one more thing, actually this constant is nothing but actually equals to e to the power del. Okay, e to the power del you will get. So So if ratio of successive amplitude is nothing but e to the power del, okay, like that you can also write. Okay, everyone. Now single degree freedom damped vibrations. Okay, damped vibrations you will discuss next. Okay, everyone. I hope this point is clear. Right. So damped vibration we have already discussed, but we'll discuss the forced damped vibration. Right. Forced damped vibration. So we'll mention here forced damped vibration. So actually a small change will be there in our system. Here a force will be acting, F equals to F naught sine omega t. Now here you should understand this omega is nothing but the force frequency. Force frequency it is, right? F naught it's the maximum value. Clear, everyone? So I hope this is clear. The stiffness is what K, damping coefficient C. Now how you will write the equation of motion? Equals to F naught sine omega t. Clear, everyone? Is there any doubt up to this point? Any doubts? Please tell me fast. Okay. Now actually in this previous case, first of all you look at the previous case here. We are having the equation like this. Here equals to 0 is there. So only complementary, see actually it is a second order differential equation, no? So equal to 0 basically means complementary function we have to solve, right? No particular integral. In this case, but in this case we are having particular integral also. If I have to write the solution here, I will write complementary function plus particular integral. Now complementary function we have already solved, okay, for that we have a solution, and that too you should understand that the solution, in that solution amplitude decreases exponentially with time. So actually we don't need to worry about that thing, because ultimately it will decrease with respect to time and at some point of time it will be 0. But we have to worry in the case of forced vibration. The forced vibration Pi will have a value, okay, Pi will have a value, right? Pi will have a value, and that value will be what? Independent of a time. If you solve the solution, final solution is what? Independent of time. That's why we are calling it as a steady state vibration. Complementary function, if you see, it is decreasing, its amplitude is decreasing exponentially with time, but in the particular integral it is independent of a time. So that is what more problem we are facing because of the particular integral solution we are getting. So we'll not discuss the CF part, we'll focus on the PI only, right? So if you solve the PI part, final solution I am writing, okay, final solution I am writing, it is like this: A sine omega t minus phi. Okay, don't worry about this one. Actually the particular integral solution is there, in which A we need to understand. A is the amplitude here. That we need to see, because this amplitude is independent of time, right? That is the most important point. See, A value equals to, remember everyone, F naught by K one minus R square whole square plus 2 psi R whole square. Right, this is the formula. Amplitude of steady state vibration, one of the most important parameter as far as the numerical is concerned. Amplitude of steady state vibration. Yes or no? Is this point clear, everyone? Is this point clear? Amplitude of steady state vibration. Right. Now in this analysis only, there is one more factor here that we need to discuss, is the magnification factor. Okay, I hope this point is clear. First of all, please tell me up to this point, amplitude of steady state vibration is clear, right? Okay, now we'll move forward here. See, magnification factor. In magnification factor, what is there? Amplitude of steady state vibration divided by static deflection, right? So this formula MF will be like this. Okay, so actually you should understand static deflection is what? The F naught by K, and in the numerator of the amplitude of steady vibration it is there. So the final relation you will get like this. And you should understand here, first of all, R is the frequency ratio, omega divided by omega n. R is the frequency ratio, psi is the damping factor, C by Cc, right? So this is the point. Now this formula again very important from the numerical point of view. Now in this formula you should understand some important points, like magnification factor is a function of frequency ratio and damping factor. Frequency ratio and damping factor, right? This is the point. Now if I ask you if the damping factor is constant, at what value of R magnification factor is maximum? For that, what you will do? You will simply differentiate the magnification factor with respect to R and equate with 0. Whatever R value you will get, at that value of R, magnification factor value becomes maximum. Yes or no? Clear? So that R value you should understand is nothing but 1 minus 2 psi square. At this value of R, magnification factor becomes maximum. Okay, you should remember this point. The value of R for which the magnification factor is maximum, 1 minus 2 psi square. Right? Note down everyone, please. These points are what very important as far as the GATE exam is concerned. Directly you can expect a numerical from these points. Directly you can expect a numerical or the questions from these points. Okay. So R value under 1 minus 2 psi square, and at this value the magnification factor becomes maximum if I have assumed the psi value constant. Clear? Any doubts till now? Okay, now I think you have heard about this resonance condition, no? So what will happen at resonance condition? R equals to 1 is what? The resonance condition only. Omega equals to omega n, like this. What will happen to magnification factor? Put if R value, if you put 1, this will become 0, only this one will be there. Okay, so you will write magnification factor will be 2 psi. So remember this point, magnification factor will not be maximum at resonance condition. Generally what will what will imagine na, that at resonance the everything is what? Maximum. No, it is not like that. Magnification factor is not maximum at resonance, it is maximum at this value of R. Clear? Which is slightly less than 1. Okay, so magnification factor is what? Not maximum at resonance, it will be equal to 1 by 2 psi. See, another point, if damping factor is 0 and R value equals to 1, in that case magnification factor will become infinite. See, damping factor 0 basically means no damping. R equals to 1 basically means resonance. So if the resonance condition is there for the undamped system, in that case only magnification factor will be infinite. Not in every resonance condition. Resonance condition without any damping is there, no, then only you will have this magnification factor as maximum, or we'll say the infinite only. I hope this point is clear. Please write down these points in your notebook. Directly you can expect a MCQ, MSQ and NIT also from these points. Everyone. Okay, done. Next, transmissibility. Very, very important point, transmissibility. Actually, see, transmissibility, first of all, we will write the formula here. Okay. Before writing the formula, we should write down its meaning actually. Force transmitted. Force applied. So actually it measures what the performance of vibration isolating system. It measures okay, see, I will tell you this thing. Okay, okay, just a minute. Cannot add more. No, okay, I will discuss that point here itself. Here itself I will tell you. Okay, now see, actually what will happen. See, I will discuss one case and from that you can easily understand the other case also. Let's suppose this is the case and let's suppose it is under static equilibrium condition. Or the mean position we can say. Now see, now if I displace the mass, if I disturb the mass, okay, what will happen? The vibration will set up, vibration will start in this case if I disturb the mass, right? So obviously what will happen? Try to imagine what will happen. It will go like this. At some point it will stop, okay, at some point, and if it is there, so extreme position it is having right now, it is at extreme position, so some potential energy will be stored and that will be converted into kinetic energy and it will again return back. Will it stop here? No, it will not stop here, it will again go back here, then again it will come back to the mean position. Now this is what known as the one cycle. This is what known as the one cycle. Okay, so actually what will happen, you will see like this. So this is what the one cycle, from mean position to extreme, then again mean, then again extreme, then again mean. So like this you will have the case, right? So that is what we are calling it as a vibration. Okay, so this is for the undamped case. Similarly it will be there for the undamped for the damped case also, right? So now this is what the amplitude, you can say x, okay, and you can say this is the time. So here you should understand, there is the, this is what the one cycle we are having, complete one cycle. This is what we are having as a complete one cycle from here to here. Clear? I hope this point is clear, right? Like this the case will be there for the damped case also, right? Okay, I hope this is clear too. Right, now we'll come back to this transmissibility part, guys. We'll quickly cover this transmissibility also and we'll discuss some parts. Okay, now force transmitted divided by force applied, and it is having a formula like this. Okay, this is the relation for the transmissibility. Clear, everyone? This relation is for the transmissibility, and you should understand, I think we have not written this point, measures what performance. Okay, it measures the performance of vibrating oscillating system. So now again this formula, if you see the transmissibility formula, it is again a function of R and psi. Again it is a function of R and psi. So some important points we will note down here for this case also. Like for R value equals to 0, if I put R value 0 and R value root 2, I will get the transmissibility as 1 for any value of psi. For any value of psi. Clear everyone? Yes or no? Right? One more case from which in the gate you will see 2 to 3 numericals they have asked. If damping is not there, that is psi value 0, the TR value will become 1 upon plus minus sign. Remember this plus minus sign, 1 minus R square. Because obviously the ratio cannot be negative, no? So plus minus sign you have to take care of this thing. Plus minus sign you have to take care, either it can be positive or it can be negative, right? It depends that the ratio cannot be negative, right? Okay, so remember this point. So these two cases you should remember. Next, this diagram, most important diagram, you should understand this. Okay, now see, this diagram is what very important, guys. So actually if you see, these are the damping factor lines. These are the damping factor lines, guys. Okay, now in this diagram you need to understand very important point, guys. So this is what we are having as the R value as 1 and this value as R value root 2. Okay, R value as 1 and R value as root 2. So we have to focus on R value root 2 only. So I will remove this one. Okay, now see. So actually what will happen, as the R value is greater than root 2, there are two regions actually. There are two regions, R greater than root 2, R less than root 2. Less than root 2 and here R greater than root 2. Now actually two cases will be there and you need to understand which case, in which case what is happening. So let's suppose if R is greater than root 2, what is happening? As the value of psi increases, damping factor increases. As the value of psi increases, damping factor, as the value of psi increases, transmissibility increases. That is what a very bad part. That is what very detrimental part to our system. But in this case, as the R value is less than root 2 and if you increase the damping, damping increases here like this. In this case, damping increases like this. So damping increases like this. So obviously transmissibility ratio decreases with the help of damping. So here damping is advantageous and in this case damping is detrimental or disadvantageous. So okay, I will tell you like this. Like this, the damping value increases in this case and in this case damping increases like this. So damping is advantageous. Here damping is detrimental, or we can say harmful also. Damping is harmful. Clear everyone? Right? So in this diagram, from this diagram you can understand, if the R value greater than root 2 and if we are providing more damping, it will affect the system negatively, right? Now if R value less than root 2 and if you are increasing the damping, it will affect the system positively. It means transmissibility ratio decreases. In this case, transmissibility value increases. That's why we are saying it is harmful or detrimental. Clear? Now moving forward here, right? Next and the last topic for today's discussion is the cam and follower. Okay, the last topic for today's discussion is cam and follower, right? Now see, actually the cam and follower, we are basically focused on the displacement of follower, right? We are focused on the displacement of follower. Okay, displacement of follower actually. So let's suppose displacement of follower is represented with y, and we will define the displacement of follower as a function of theta, where theta is crank rotation, or sorry, not crank, we have to say the cam actually, cam rotation in radian. Okay, cam rotation in radian. So displacement of follower y equals to as a function of theta, right? This relation we have to establish during the analysis of cam and follower, right? This is our task here, to establish the relationship between the displacement of your follower with the cam rotation. That is what the task we need to do during the analysis. Now, if it is the displacement, I can easily calculate velocity. Or in some cases, they will directly give this relation also. So, you should understand how you can utilize this relation. Dy by dt is there, so you will have like this. Dy by d theta you will do, and here d theta by dt. D theta by dt is nothing but omega. Omega, that is rotation of cam, multiplied by dy by d theta. Similarly, you can calculate the acceleration also. See, again, velocity is a function of theta here now. So we'll differentiate theta. We'll use the d theta like this. Again, omega square d2y by d theta square. Now, this is the one parameter, acceleration. Now, next parameter, very important one, is the jerk. J equals to dA by dt. Right. So here finally, if you use dA by d theta, it is there, multiplied by d theta by dt. dA by d theta and d theta by dt like this, and you will have the jerk omega cube, you will have d3y by d theta cube. So this is the relation, guys. Remember, velocity of follower we have calculated, acceleration of follower we have calculated, jerk of this follower we have calculated. All these important parameter we have calculated. Now, actually, what we'll do here, four different cases are there that we need to discuss here, like case 1. And in each and every case, you need to remember the formulas, like velocity formula, maximum velocity, maximum acceleration, like this. First case, uniform velocity. Okay, uniform velocity. In that case, the velocity formula we should understand, and obviously the acceleration value is 0. Clear, everyone? First of all, tell me, in this one, any doubt? See, this relation we need to establish. That is what the task. Okay, that is the main sole purpose of the analysis of cam and follower. Is there any problem in this case in order to calculate the velocity and acceleration and as well as the jerk? Tell me, everyone. Clear? Okay. So we are calculating uniform velocity. Obviously, acceleration will be 0 because the velocity is constant. But the formula you should remember, h omega by theta. Now, theta, if they are asking the velocity of ascent, angle of ascent you have to put. If they are asking the velocity of descent, angle of descent you have to put. Clear? Now, case number 2. Uniform acceleration. Now, in this case, you should first write the velocity, maximum velocity formula. and then acceleration formula. Now see, there is a one important point. During acceleration, what will happen? During acceleration, what will happen? See, we are saying uniform acceleration, but you should understand, follower will start the motion and it will come to the extreme position, right? But from starting to the end, acceleration is constant. How is it possible? From starting to mid, it will accelerate, but after that, it will retard, but with the same magnitude. From starting position to the mid position, positively accelerated. From mid to extreme position, negative acceleration. But the magnitude is what constant. That's why we are saying uniform acceleration. And throughout this, from this beginning of the stroke, beginning of the motion of the follower to the end of the motion of the follower at the extreme position, where the velocity will be maximum? Tell me. Where will be the velocity maximum? If the follower start the motion from here to some another extreme position, where, at which point, at which location the velocity will be maximum? Please tell me fast, guys. Where will be the velocity maximum? Obviously at a mid stroke, right? See, it starts from the motion here. Let's suppose this is the starting point of the follower motion. It starts, and at the mid, okay, it will change. So from starting to the midpoint, it will accelerate, positive acceleration, and after that it will negative accelerate. So at the mid only it will have the maximum acceleration, or maximum velocity actually, not the acceleration. Acceleration is what the constant here. Okay, now see, the formula will be 2h omega divided by theta, and here it will be 4h omega square theta. Right, everyone? Okay, right? So h omega by theta, acceleration 0, 4h omega square by, obviously this is the complete square actually. This is the complete square. Okay, like this. Next case, case number 3, SHM. Tell me the velocity formula and acceleration formula, guys. If anyone knows, please tell me. And the last case, cycloidal. Again, velocity formula and acceleration formula. See, these formulas you need to remember anyhow. Anyhow, you have to remember. Okay, otherwise, see, they will directly ask the question, and if you are not able to recall the formula, then you will not be able to solve. Okay. Okay, here we are calling it the velocity, maximum velocity we are writing. See, h by 2 pi omega theta. Okay, just remember this one, and if you want to remember the acceleration one, just square this one, pi omega theta square. Okay, like, see, if you try to observe this one, no, just twice it is there, but omega by theta whole square is there. Remember this thing. And in this case also, h by 2 pi omega by theta, h by 2 pi omega by theta whole square acceleration. Right, like that you can remember the formulas of the velocity in the acceleration case. Right? Right, everyone? Now, last case, cycloidal. Actually, what is cycloid motion? Can you tell me what is cycloid motion? A point, a locus of a point on the circle which is rolling on a horizontal line. Right? Locus of a point on a circle which is rolling on a line. Okay, that locus will be nothing but the cycloid. Okay. Right, again this maximum velocity only, 2h divided by omega, 2h omega divided by theta actually, 2h omega divided by theta. Now tell me, what will be the value of acceleration? See, the formulas you should recall. If you are not able to recall, then there is a problem. Okay, you have to recall. Anyhow, you have to remember. Daily you have to revise the formulas, because again, lot of formulas are there. in theory of machine also, like subjects like fluid mechanics also. So every subject will contain lot of formulas. You will be able to solve the numerical only when you will be able to recall the formula. Everything you know, every concept you know, but if you are not able to recall formula, then there is no use of the concept, right? You cannot derive the formula in the examination hall. It's all about the time, right? Within given time you have to solve question. It's not like that, okay, you can solve the question at any given time. Whatever the time given in the examination, in that time only, within that time frame only, you have to solve the question. That is what creates the pressure on the aspirant. That is what creating a pressure on the person who is sitting in the examination hall, right? The time is actually creating the pressure. So we have to work in a such a way that will not get a pressure from just by looking at the clock. Okay, so we have to practice the All India mock test series, right? Okay, so here the formula you can write like this: omega by theta square, h into 2 pi omega by theta whole square. Okay, any doubts? Right, theta you can place for angle of ascent, angle of descent also. It depends whether they are talking about ascent or descent. Actually what happens, see, if I tell you, initially what will happen, the follower will move like this, then there is a dual period, then there is again what a descent. So actually see, so I've drawn this cam follower case here. Now let's suppose that if it is rotating like this, omega. So what will happen? The follower will move upwards. So there is a minimum position of a follower, there is a maximum position of follower. Between that it will move, and that is what known as the lift of the follower also, right? That is what known as the motion of the movement of the follower. Now try to understand a point here. When it is at this position, beginning of the movement of the follower motion is there, and it will come to this point. Now at this moment it will remain there for some time. That is known as what the dual period. When it is moving from here, from bottom to top, so that period is known as ascent period. When it is going coming from top position to bottom position, that is known as what, the descent period. I hope this is clear, everyone, right? Is there any doubts? Okay, so this is what you should remember here, and these formulas are what very important with regards to cam and follower, right? Now we have discussed all the possible formulas, all the possible important concepts, tricks that will be what useful for your GATE examination, right? Now just revise whatever you have done till now and have the confidence over that. See, it's not like that if you have prepared you will get the marks. You should also have the confidence. Sometimes in the pressure only you will do the silly mistakes. You should have the confidence, whatever you have prepared, that is what sufficient, and whatever you have prepared, from that only you will get the good marks. From that only, whatever you have prepared till now, from that only you will get the good marks and a good rank. You should have that much confidence. Okay, while revision you should be what, more confident. Whenever you are revising more and more, you should be more confident over your preparation part. When you are confident on your preparation, no, then definitely you will get the success, right, everyone? So I hope this session is what helpful to you, and it will give definitely benefit to you in your preparation part. And from my side and from my team, entire mechanical team, all the best for you for the GATE examination, and thank you so much